Okay, so I'm Philippe Citroën, Director General of UNIFE. I'm honored to be with you today for the kickoff meeting of this promising NextGear project, Shift to Rail. I know that the Shift to Rail project officer, Javier Ibanez, is program manager of Shift to Rail, is with us. And in fact, we shouldn't call it anymore Shift to Rail, but EOP's Rail Joint Undertaking. You know, this is the new name, and we'll have the opportunity to say a few words about this a bit later. In fact, I was very happy to be invited to the closing ceremony for this important program, which is called Next Generation of Method, Concepts and Solutions for the Design of Robust and Sustainable Running Gear. Because I had the pleasure during the 5 years of journey of Shift to Rail to attend all the kickoff meetings and the closing meetings, and I saw how successful this project was, and that's why the council, the commission, and all the public authorities were very supportive of the successor of Shift to Rail, which is called EOP's Rail Joint Undertaking. We were also happy to say that in this project, there were a lot of project members, main contributors. We had academic centers, institutes, the rail supply industry, a metro operator. And this is part of the success of Shift to Rail, because it was the first time that in the same research program, we had the opportunity to have at the same time the operators, the infrastructure managers, the rail supply industry, the universities, and the SMEs, which are also a big part of this research program. So the list of the partners is quite impressive. We see that we have UNIFE, KTH Royal Institute of Technology, the University of Huddersfield, Politecnico di Milano, Lucchini, the University of Leeds, Universitat Nebrija, NIT SRL, the Metro de Madrid, the Autority Ferroviaria Romana, the Romanian rail authority, the University of Nottingham, we have Bercela, Delner Dampers Actiel Bolag, Statens VAG, OCH Transport Forwarding Institute. So it was quite impressive to have those universities, research centers, and UNIFE plus the rail manufacturers were part of this very important program. Well, I think that, you know, that since the new commission was in place, the motto was now we have to build a Green Deal for Europe, and achieving the European Union Green Deal objectives, thanks to projects like NextGear, which will certainly contribute to the reduction of the weight and consequently to the requested power and the energy consumption. And that is very important because since Madame van der Leyen was elected as the chair of the European Commission, the Commission is really pushing a direction on these topics of climate neutrality, and the rail sector is showing that it can bring a lot to the work the Commission is pushing for having this climate neutrality by 2050 and by having a reduction by -55 from now until 2030. So what were the NextGear objectives? The NextGear project has explored the technical developments for the future running gear, looking into ways to design trains that are more reliable, lighter, less damaging to the track, more comfortable and less noisy. The project develops across three thematic work streams, and you know better than me. We had the point one was a universal cost model, 2.0. The second point was the high-end solution to the development of running gear innovations. The point three was how to have the wheel set of the future. Then you had to work on the universal cost model, which has made the evaluation of the benefits of the proposed innovation. But after that, you had the high-end solutions, the development of running gear innovation, which has explored the use of new materials and manufacturing process to reduce the weight of the bogies. That has always been central in the discussion and the work of Shift to Rail. Then we had for the wheel set of the future, we had the investigation of the use of composite materials for future development. In this case, of the axle of the wheel set. And then we had you remember the interactive work streams, the development of the cost model, which was supposed to look at the innovation proposed in the other work stream to measure this point. The results, from what I understood from Jose, who has been with you, Jose Bertoni, who's been with you from the very beginning of this project, I think that the NextGear consortium has exceeded all the expectations at the beginning of the project. Although it's low TRL, the consortium has been capable to design, to develop, but to manufacture and test different elements of the train with new materials and manufacturing methods. That was extremely important. It has also investigated the potential use of composite materials for the development of the axle of the wheel set. And all these innovations were economically evaluated in the new upgraded, more precise and user-friendly release of the universal cost model tool that I've already mentioned a few seconds ago. However, as it is always the case in research, it is not and must not be the end of the road, and we are totally convinced that there will be new opportunities in the coming future, thanks to the new Europe's Rail Joint Undertaking, particularly in one of the flagship area. You know that next week there will be the official inauguration of the Europe's Rail Joint Undertaking in Paris, because now we are during the French presidency. That will be very important. And you know that this ERGU new joint undertaking was extremely successful, because there are now 25 founding members, 10 coming from the industry and the others coming from the railway undertaking and infrastructure managers. The budget of Europe's Rail Joint Undertaking went from 920 million euros to 1,200 million euros. There is a real motivation from all the rail sector to work, and the most important tenders will be launched in a few weeks from now, and the Commission hopes, at least for the first part of ERGU, to start the first program, let's say before the end of the year, because we are not very happy with these discussions, which were quite long. And in fact, everything is going to start at the end of this year. But you know that there will be a presentation soon by the Commission of all the flagship areas, but it's already available on all the website of the ERGU. So I would like, of course, to thank my speech by saying that we were very happy to see the partners' involvement, and I would like to congratulate them for having made NextGear a successful project. I would like also to thank the joint undertaking, and especially Javier Ibanez for the support he gave to us on NextGear. And we really hope to have the opportunity to continue our collaboration in the future ERGU. We will see now what will happen in the next weeks, but as far as I'm concerned, I would like really to say that this program that you have managed was extremely successful, and it's part of the success of ERGU, because when the Commission made the evaluation of Shift to Rail, they wanted to be sure that the project where the industry, the operators, the infrastructure managers, and the university have been part of it were successful. So again, thank you very much. I hope you will have a nice meeting today. I'm sure it will be the case with Jose and Javier, and I wish you all the best. And I will stay with you a little bit, but it was a real pleasure to be with you. I'm sorry I didn't take my normal computer, but there was a bit of a problem today, but I hope it was okay for you and you could see and hear me well. So thank you very much.
Okay, thank you very much, Philippe, for your welcome and your kind words. Essentially, I think that all the people around can we agree that we are really enthusiastic to continue with Europe's rail in the future. But okay, there will be time in the presentation of Javier to talk about this. Before going to this presentation of Javier, I would like to provide you some information, practical information regarding the meeting. My name is Jose Bertolin, the project coordinator of NextGear, and I'm going to be the moderator of this event. As you can see or notice, this event is a streaming event. So it means that you are not able to use your camera and your microphone. They are going to be unable. So if you want to ask any question, I would really recommend to use the chat tool that is in the platform and to make your questions as soon as they come to your mind, because in this way we can manage them roughly and we can address it to the speakers, because we need to manage a potential gap between the live and the streaming. So I really appreciate if you can follow in this way. Okay, as you can see in the screen, we have the agenda of today, and the next presentation will be the one of Javier Ibanez, the program manager of Europe's Rail. Then we will continue with the overall presentation of the project from myself as project coordinator and Sebastian Stichel, the technical leader. And then we will have 3 main blocks regarding the technical innovation of the project. In the first one, we will tackle this high-end solution to develop the running gear innovation. Okay, and afterwards, if we go to the next slide, we will see the presentation of the wheelset of the future. And we will finalize with the UCM, it means the Universal Cost Model. Remind you that there will be a break around 11. I hope that this delay is not going to impact it, but essentially during this break, you will have the opportunity to watch a video that we have prepared with the main outcomes of the project and with some interviews of the main participants on it. So in order to not make it longer, I would like to give the floor to Javier Ibanez, the program manager of Europe's Rail. Thank you, Javier, for participating today.
Thank you. Thank you very much, Jose. Thank you very much also, Philippe, for your kind words. I just need to say that, I mean, the success of the Shift to Rail program and the success of now in Europe's Rail wouldn't have been possible without the collaboration and the participation of all of you, of all the railway stakeholders, the companies, the universities, the university research centers, everyone that has been contributing to the success of the program is, of course, are the ones that made this success possible. No, so in that sense, thank you very much for the work. But I mean, I'm just another piece in the chain that made this work as it was expected to be. No, so having results at the end of the program, and of course seeing this continuation in this new GAU that is going to be launched, as Philippe mentioned. He's made a very good summary of all the topics going on. So I just adding to his words, just mention to you that the launch event will be, as Philippe said, next Monday, and you will be able to follow it online. So be connected. I mean, follow the social media channels that from UNIFE, from Shift to Rail, and taken from Europe's Rail. You will have the possibility to join this event if you're interested. And of course, this work that you have been carrying out in a specific, parts of in this case, within the IP1 or the innovation program, under the umbrella of the innovation program number 1, more related to rolling stock and the developments on the different subsystems that involved, has been successful and impactful also in the collaboration with the Call for Members project that have also a big role in the program. But just going into the main remarks that I would mention. I mean, I still remember when I joined the kickoff meeting back in December 2019. There was at the time even another coordinator for UNIFE. So things have changed, and of course the way all these activities have been carried out have changed. I mean, due to the situation we are still in, but even with these constraints in the way we have to adapt and to accomplish the activities set in the DOA at the end, in the ground agreement. I can say, and from the program management point of view, that the collaboration has been always good, open, this was reflected, of course, in the first reporting period of the project. As you know, the project, you will have the details later on, but it has two reporting periods. The end of the project is by the end of December, by the end of February, so in a few weeks. And based on that, we still have to assess the second part of the second half of the project. But based on the results you achieved during the first half of the project, I mean, and based also on the project that you have been carrying out within this second part, I may say that, I mean, the collaboration between you, also the collaboration and the exchanges with the JU have been always good and has been always fruitful, no, for all the parts. So from that point of view, I just want to congratulate you for the work done on the different specific topics you've been touching upon: the universal cost model, the wheelset of the future, all these developments and progress in the way things are produced and manufactured in order to reduce the weight of the rolling stock that is so important for these global KPIs, the Shift to Rail program and the future Europe's Rail JU will be touching upon, are important topics, and of course at the end have results and also affect, you know, at the end the people for whom we work and for whom we would like to see these solutions at the end be seen outside. No, so at the end, the customers and the people who is at the end taking the trains and who might not see these innovations going on, but feel that the sector is moving, is the one of the objectives that we are here for, to provide these developments and these solutions for the outside world and for the market update at the end. That is the one. Or that is the judge at the end saying that if the program is providing a good result, these results should be also be seen or be noticed in the outside world. Usually, as Philippe was mentioning, this is, of course, these are innovation activities, these are innovation projects. So some of these progresses and results might not be as good as we would have expected, but also by innovating and by noticing which are the paths, or modifying the paths in order to go to the proper innovative solution. That's also the way to get to know how these implementations can be further used in the future. So from that point of view, I will be happy to be joining you as I join you for the kickoff. And due to the situation, it hasn't been possible for these more face-to-face interfaces. It's not only with this particular, with NextGear, but it's been like this in the last 2 years. Also for you has been difficult, because I know well that when you have to carry the test and you have to interact, sometimes it's better to have this face-to-face, this socializing part of the project management is very important, and we have also noticed that. But even in this situation, I can say that the spirit has been always there, and it's been always there in all the projects. So that's also something we have to value and to have present for the for the future innovate, for the future participations you may have in the future calls of Europe's Rail, and we are here to support you. So from that point of view, I will be just here in this supporting role, and of course in this more administrative side of the project when it takes the time to be assessed and to assess, of course, the results. Just one point also to mention that is very important, and maybe as we still have to assess this second half, as I was the second half of the project, as I was saying before, the dissemination part of the project of the results are very important, as you know, for the program. So, and also as stated in the grant agreement, in the DOA, this work that you have been carrying out, it is not publicly exposed in conferences, in forums, through publications, through scientific papers. It's important that you, as the project executors, have to provide this dissemination of the results as much as you can. As you know, there is also a collaboration or still a link with the program for the coming years. So in case these innovations now, in the future, in the coming 2 years, are somehow having an effect or having or receiving the interest from the stakeholders interested in using them, that is also your opportunity to not stop in here. I mean, this is the end of the project, but I mean, all the results you have been, all the results that you will show today, and all the outcomes of the project have to be still promoted in the years to come. So from that point of view, just point out that dissemination of results, and of course the involvement of this part of the activities in the project is very important. And from that point of view, I push you to in your website, in the dissemination channels you have, to make this publicly available and show these results outside. Also, thank you very much for the collaboration you had with the funding, with the calls, with the projects, also in which the members from Shift2Rail are also involved. They also see, and I've always said since I joined the JU, that the collaboration or the link with the work the open calls are doing, and how this is reflected in the work of the call for members is done, is very important. And it's also, thank you from that point of view, because it's always valued, and it's always maybe not recognized as it should be sometimes, but we have to acknowledge that, and that's a very important issue to be also stated here. But that's a bit of the introduction I wanted to make. That I'm here open for any questions you may have, any things that in the coming weeks, but as we will have to process everything. But I'm here open to any questions and any thing you may have. I'm always happy to help. So thank you very much, and have a good meeting.
Okay, thank you very much, Javier, for your kind words, and also for emphasizing the dissemination. I can inform all the community that we have had a really fruitful dissemination in the project, due to the involvement of the research centers, academia, that they are really keen to disseminate their activities. So we will include in our website all the dissemination, all the articles that we have published, all of them, most of them are open access. So I hope that we have to promote the project, to communicate well, and this is a very important message. In addition, we will keep an eye on the website of Europe's Rail in order to be able to participate in the future, because I think that I am not lying if I say that all the partners of the project are really, really interested to participate in this new initiative. And for sure, I think that the project deserves a new opportunity due to the really important result that we have, and also to improve the maturity of the solution, the technologies. Now it is TRL 4.5. Although I can tell you that we can go beyond this TRL in some cases. And I think that in the coming future, all the partners of this consortium will be available to continue working. So thank you very much, Javier, again, for your kind words. Okay, so going very fast because we are having a bit of delay. I will continue with an overall presentation of the project. There are some messages that has been already mentioned in the two previous presentations, so I will go very fast through my slides. I'm going to share my screen. So, okay. So as it is mentioned before, the NextGear project is a Shift2Rail project. It is an open call. It means that the consortium is consolidated by companies that they are not members of Shift2Rail, and it is allocated in the IP1 Innovation Program 1 that is related to the cost-efficient and reliable trains. The project has been funded 100% due to this is a research innovation action with a budget of 2.6 million euros. It was also mentioned that due to the pandemic situation, the project didn't end in the planned deadline. It means November 2021. So we are finalizing now in February 2022. So we are accumulated 3 months of delay, but it has been due to this lockdown and the impact in our activities. The consortium is constituted by 16 partners, and I would like to highlight with this slide the number of countries, of member states that has been involved, from the Western Europe, for the Eastern Europe, even from the center. Okay, so we have a really long list of partners from different expertise, different areas, background. But the good point is that all of them has collaborated really, really well. And okay, we have had a very, very promising results in the innovations. Okay, I am not going to enter into many details regarding the consortium because it has been already highlighted by Philippe and also by Javier. But just to mention that 50% of the consortium is constituted by research centers and universities, and also it is important to mention also the participation of the rail supply industry, not only the UNIFE associations, also companies as Lucchini, NEET, Delner, Bersela. Okay, we have created a good consortium to have a very successful results. In the last point, I would like to mention Metro de Madrid, that has been contributed with their expertise and the infrastructure for the test in the real environment. You know, well-known Metro de Madrid operator that is well-known and well-trusted. So regarding the high-level objective, with this slide, I wanted to highlight 4 of them. In the central, we have the UCM. As it is mentioned before, this tool is used to assist all the innovation to evaluate their benefits from the economical point of view, but also considering the technical aspects. It has been a great for the first tool developed in rail-to-rail. And regarding the different other activities, we have also mentioned the novel materials and manufacturing methods with not only the investigation of them, but also the manufacturing and test of different elements of the running gear that has been selected based on a previous survey. In a second step, we have another important high objective, that is the active suspension, that, as you know, it has been investigated in the latest decades, but unfortunately there is no consensus and acceptance of this because there are still some uncertainties, some limitation that needs to be tackled. So in this project, the partners go a bit further with this hardware in a loop demonstration for the controllers, for the active suspension, and also with the manufacturing of a prototype, an actuator regarding the active secondary suspension. Last but not least, we have the wheelset of the future, that is also have a really promising results. We investigated composite materials that can be used to the manufacture of the wheelset, and in particular, we analyzed the axle that joined the 2 wheels. So finally, regarding the project structure, okay, as it is mentioned before, the readiness of this project is TRL 4 and 5, although I think that we have exceeded this limit and we have achieved very good results, even with some test campaign. But the project at the beginning aims to continue the activity of roll-to-rail and rail-to-rail, and it is divided in these three work packages already mentioned, and had a very good collaboration with Pivot 2, the complementary project, essentially in the universal cost model, but not only on that, also with the review and follow meetings in order to check the progress in the project in the work package 2 and work package 3. So this is more or less the global picture of the project. Now I would like to give the floor to Sebastian, technical leader of the project, to present the objectives and the main results and achievement of the project. Sebastian, the floor is yours.
Thank you very much, Jose. I'm also going to share my slides. Okay, yeah, Sebastian Stichel from Royal Institute of Technology in Stockholm. Good morning, everyone. short presentation on the technical objectives and achievements of the project. And I would like to start with positioning our project in the general shift to rail context, with mentioning the main objectives of shift to rail that we worked on in this project. Definitely very much on substantial reduction of life cycle costs, improved reliability and energy efficiency of trains, enhanced capacity, for example, when it comes to amount of passengers, reduction of noise emissions and other externalities, and achievement of full interoperability of the rolling stock. One issue that was discussed very early, I remember, in the setup of the Shift to Rail program, was that the take-up of innovations that were suggested in research projects was not satisfactory. A lot of innovations were proposed, but often they were not implemented in vehicles. And one of the reasons was assumed to be that innovations sometimes have the tendency to increase the first cost of a vehicle, and that is to be paid by the operator, while the benefit, which often is reduced track deterioration, is with the infrastructure manager. And another issue is that the life cycle costs over the life of 30 years are calculated, but are not so easy to calculate. So in the end, often the first cost is still very dominating for the decisions. Therefore, it was decided very early in Shift to Rail to develop a so-called universal cost model that should have the possibility to show the cost of, for example, a bogie with an innovation throughout the whole life, and by that showing that innovations really also can reduce the cost for the whole system. And that was one of the important parts of the project. I don't need to repeat the work package. I think they were mentioned 2 times. I just want to mention that we changed the order today in the presentation because we found it's a little bit more logical to start with the technical innovations that we have worked on, and then finish with showing what they can give in the cost calculation, then in the end with the updated universal cost model that we have been working on. What did we say from the beginning? What did we promise in our project application that also, of course, is based on the call that was out? What we said is that we will update the universal cost model so that it is accepted by as many stakeholders as possible in Europe and also used. It should be much more user-friendly than the one that was developed in Roll to Rail, because in that project, that was one of the first projects in Shift to Rail, the first version was developed, but it was not deemed to be user-friendly enough, and some of the modules were quite basic when it came to calculation methodologies. We were to work on new solutions when it comes to manufacturing techniques for bogie components. We should define requirements, specifications for materials. What does a material have to fulfill? What has a manufacturing method to fulfill to be able to be used for rail vehicles, and especially bogies in the future? We said that we will work on a number of optimized control configurations for new vehicle concepts, bogie concepts that we work on a new controller and make a hardware in the loop validation of that controller to show that it is really fit for usage in rail vehicles. Very important also the technical concept for a hybrid metal composite wheel set. And finally, explore the feasibility of in-service inspection and or monitoring of a wheel set with composite parts, because that is also essential. Otherwise, such a solution would not be used in the end. What did we work on in the end? And on this first slide here of 3, you can see that we definitely worked a lot on possibilities for weight reduction in future rail vehicles. All 4 examples that you can see here on that slide are examples of possible significant weight reductions in future vehicles. And this slide is also very illustrative for which different methods there are for weight reduction in rail vehicles. The first one, the antenna bracket with additive manufacturing, that gave a 60% weight reduction compared to an existing component, is an example of how new manufacturing methods can provide shapes that are not possible with other manufacturing methods, and by that reducing weight significantly. And that component has even been mounted, not only built, but also mounted and tested on a Metro Madrid train. So regarding TRL, I would say we were definitely in that part higher than 5. Also, we developed, designed, and manufactured a carbon fiber composite frame, and that is a second possibility for lightweighting, to change material, in this case from steel to carbon fiber material, and that frame is 50% lighter than a steel frame would have been. Also, the third example, the hybrid metallic composite wheel set, which promises even 60% weight reduction, is an example of how more advanced materials could reduce weight of future trains. And the last example is an example of conceptual lightweight design. By simplifying the layout of a train, you could also reduce the weight. In that case, by just having a single stage suspension, for example, that makes, in general, reduces the number of components and promises here a 400 kilogram per meter weight reduction for a 2-axle train set. When it comes to active technology that José also mentioned, is that we developed a new controller with sampling response frequency up to 1 kilohertz, and we validated that it definitely would work for the control solutions that we suggested for new bogie concepts, for example, for this simplified 2-axle vehicle. We also developed in the project a new type of actuator that is more sophisticated than existing actuators, and that especially is very useful when it comes to active radial steering of a wheel set in a curve. And finally, when it comes to the universal cost model, we made a completely new user interface for that cost model, which hopefully makes it much easier to use. We also added instructions and default values for baseline cases. There's a new, quite sophisticated procedure to model and predict damage in switches and crossings, which did not exist in the beginning. We worked quite a lot also on cost methods. From the beginning, there was an engineering approach, which we still have, but we compared it quite thoroughly to econometric approaches also to see, does it give comparable results? And I think that improved the reliability of the project, of the tool. And finally, with an innovative modeling approach, it was possible also in the end to test the innovations from the other work packages and also from some other shift to rail projects in the UCM to show other benefits of these innovations. And with these I would like to thank the whole team of NextGear. I think you have really done an amazing job. You were extremely dedicated to your work, made it very easy for me as a technical leader, I can say. And as Jose also said, I think the results that we have produced are quite impressive, and you will see that in the coming hours. So thank you very much.
Okay. Thank you very much, Sebastian, for this comparison between the objectives of the project and the achieved results. Yeah, it is important to mention the high level of accomplishment of the project, as you said. It means we defined it at the beginning the planned objectives, and later we have demonstrated that we have achieved them, and even we go beyond our expectations. So it is really, really important to remark this point, but because sometimes in the R&I work, it is not the case, because a project detected many issues and they have many barriers in order to comply with what was planned. So in order to receive an insight how the project really achieved these goals, I would like to give the floor to Simon, that he's going to illustrate how Work Package 2 achieve all these goals. Before that, I would like to remind you to use the chat. It means if you have any question, please formulate it in the chat, and we will be able to reply after this blog presentation. So in this way, we can address easily to the speakers. So please, Simon, the floor is yours, and we are really enthusiastic to see what happened in Work Package 2. Sorry, Simon, I think that you are muted. Please.
Sorry, I'm the first person to make this mistake today. So good morning, everybody. My name is Simon Donitsky. I'm the director of the Institute of Railway Research at the University of Huddersfield, and I've been leading Work Package 2. I also want to share my screen with you. So okay, why is it not sharing? Are you seeing my screen?
Yes, we can see it.
Okay, thank you. Right. So I will talk to you about the structure of what our Work Package 2, as Jose and Sebastian have introduced. This work package was dealing with a number of innovations within the running gear of a railway vehicle. We had aims which were set out in the description of work, and you can see them here. Mainly, we were looking at a number of different technical developments which have been bubbling around in other industries, but not used so much in the railway industry yet. For example, we were looking at ways of reducing mass to make, this is particularly important in railways, in that then reduces damage, reduces forces, damage to the track, makes the vehicle more comfortable and less noisy, and causes lower cost from lower life cycle cost from this. We've considered these innovations in a number of different ways, particularly for looking at novel manufacturing methods, novel materials, and then developing a high safety and integrity level controller so that we can introduce some active elements within the suspension. I think the project has gone probably further than we expected in most of these areas, in that we've actually manufactured prototypes, or at least proof of concept in a number of these areas, which you'll see my colleagues will present now in the rest of this presentation. I wanted to just share this with you. I know there's a lot on this slide, but I think this will illustrate the different elements of the work package and how they come together. You see here on the left side in blue was around using novel materials and manufacturing methods, and that was split into two tasks, one around additive manufacturing, Sebastian has already given you a taste of what you're going to see in terms of the novel component that was manufactured and testing. And also we looked at introducing fiber reinforced plastics, and we have a carbon fiber composite frame, which also reduces mass and improves performance of the running gear of the vehicle. Then in green here, you see the other area of our technical work, which was around the development of active control within the running gear. We developed an actuator, which will allow improved performance in curving, but also good stability, good control of the running gear, and allow a single axle running gear to be effectively implemented. As part of that, we need to have a controller. And that controller doesn't really exist in the railway field. So we developed a high safety integrity level controller, which is optimized for work in controlling railway vehicle suspension. At the bottom, tying this all together, we won't focus on this a huge amount today, but we see it as very important. Very often in innovations, in my experience in the railway, it's not the technical innovation that in the end stops something being implemented, it's the business case. So we were very keen to collect the data which would allow a good business case to be prepared, so that the innovations, the different innovations can be used by the railway industry. I'll come to the deliverables at the end. So this is the structure now of the rest of our presentation for the work package. My colleagues will explain the additive manufacturing and the composite materials section, and then the controller section. I will come back at the end and show you some conclusions from our work. So I'll hand over first of all to Ali Gorkan Demir, and Gorkan will tell you about the development of the additive manufacturing methods and how that led to a product which we could use. So I will stop sharing.
Okay, thanks, Simon. Good morning, everyone. Greetings from Milan. So I will quickly share my presentation, which I think you should be able to see soon. So it's my privilege to speak to you about what we have done in NextGear together with my colleagues in RINA CSM in Rome, University of Huddersfield, and Metro de Madrid. So we studied a new solution for railways applications, starting from a single point, which was additive manufacturing, trying to see also what sort of innovations we could supply to the railways industry. So in additive manufacturing, we have a lot of potential for different industries. In railways, these potentials have not been previously explored widely. One of the reasons is related to the fact that we have different stages of maturity. We have different stages of maturity in terms of materials available, manufacturing systems available, the sizes of the components that we can make. So for that reason, the workflow of our task actually started from something different, starting from the availability of the materials, the processes available, and then we set the scene for what we can do towards railway applications. So this is why, in order to fulfill the requirements of our project, mainly related to the fact that we want to achieve lightweight structures, we went for aluminum alloys. We went for also arguably the most mature metal additive manufacturing technology, that is laser powder bed fusion, which you can see as an animation in this slide. So we wanted to take our material, take our process, and develop a solution towards railway applications, which we found that the most suitable case for us was the spare parts. So for that reason, we wanted to see how much additive manufacturing could contribute in order to change the logistics, especially for producing these spare parts on demand. But we didn't stop there. We tried to see what options we had for case studies, and this was one of the most interesting parts of our task. So we sat down with Metro de Madrid to see what parts we could manufacture. And the digital data that we could use to manufacture that part. So, for instance, the vibration data coming from the actual trains. We exploited fully the digital manufacturing scheme using topological optimization. So this is how we also reduce the weight without compromising the mechanical stability of the component. We manufactured the component and we applied testing and validation, which I think is a good achievement, starting from a very low TRL, moving towards something quite reasonable in the given time. So I will go through the technical details and I will try to explain to you what we have done in terms of the applied work. So we have taken our material that is an aluminum alloy, aluminum silicon 7 magnesium, which is commonly used for cast parts in the industry. And this is also quite applicable to laser powder bed fusion. We worked with a medium-sized machine, and let me underline the fact that this is medium-sized for metal additive manufacturing machines, which has the capacity of producing parts with 300 millimeters in diameter and 400 millimeters in height, which is somehow limited to what components that you might need for the railways industry. In any case, we started off by studying our process parameters in order to achieve adequate density, which is essential for mechanical properties of the component that we need to make. We carried out several experimental campaigns. You see here the density results. I'm not going to go into the technical details about it, but we studied especially one important parameter for the productivity, especially concerning the fact that we want to prepare parts on demand, especially for the spare parts applications. So the layer thickness, which is one parameter that controls especially the productivity, was a parameter of our interest. So what we have done is also was related to identifying a production cycle. So in metal additive manufacturing, you essentially need to produce the part, and you need to also apply some post-processing. In terms of post-processing, we had to study the heat treatments. So heat treatment is also a critical point in logistics. The idea is that if you produce a part where you need, or if you think about the centralizing manufacturing, a heat treatment might be very tricky because of the size of the component, because of the furnaces that you need, and so on. So together with our colleagues in Rome, so CSM RINA, we studied a novel heat treatment for the railways industry. The idea was to make a heat treatment that is applicable to a decentralized manufacturing scheme that doesn't compromise the mechanical properties of the components that you make. Also considering the fact that now we're going towards mid to large-sized parts for metal additive manufacturing. So we don't want part distortions. We don't want any geometrical failures during the heat treatment. This is, for that reason, we studied a large experimental campaign also for heat treatment process parameters. We varied the layer thickness, as I have said before, and my colleagues in Rome, they studied also new recipes for heat treatments of this alloy. Going quickly into the details, my colleagues in Rome, together with us, they studied the heat treatment options, starting from a standard aluminum alloy heat treatment that is a T6, and the standard heat treatment, which could be applicable to conventional aluminum alloys. It considers a quenching process in water, which might be also somehow detrimental for large parts, as that might bend and get distorted during this part. They also considered a direct aging treatment and a modified T6 treatment. You can see the process parameters in detail, but the idea is that we were aiming for adequate mechanical properties, but also trying to figure out a way that we could make the whole heat treatment process easier for a decentralized manufacturing. For that reason, we also considered whether we can reduce the gas consumption during the heat treatment, whether we can do this in air atmosphere or in argon atmosphere, which would potentially increase the costs of the heat treatment. Very quickly, going into the final recipe of manufacturing of this alloy for railways applications, we said that we will go for a quicker manufacturing in laser powder bed fusion by increasing the layer thickness, because we found out that the mechanical properties were still adequate after a heat treatment in air atmosphere, because once again, we found out that the mechanical properties were still suitable. And the heat treatment was a direct aging heat treatment, where my colleagues showed that the mechanical properties were very well. The post-processing time was reduced. We avoided quenching, and this is potentially good for the distortions which might happen during the heat treatment. So this is one of the achievements of our task. We tailored the heat treatment for railway parts produced by metal additive manufacturing. We then actually, in the meanwhile, we studied different parts which we could produce by the laser powder bed fusion technology. And our colleagues in Metro de Madrid, they provided us with 7 different cases. And the first limiting factor was the size of the components. Here you see the way that we tested these components in a virtual world to see whether we could produce them by the process and the machine that we have. In the end, we identified the ATP antenna bracket, which was the final component that we produced and studied, which was suitable for many different aspects in terms of the size, in terms of the complexity of the part, and in terms of what we can innovate within this part. So I will go through the stages of how this part was and what it became by the end of the task. So our part is actually something that is hidden within our train. It is made of steel. It weighs 26.2 kilograms. It is made of some very conventional manufacturing techniques. We're speaking about sheet bending, cutting, welding, and bolting. And we have 18 components in order to manufacture this part. So the idea is we took this part, we used the actual vibration data of the train, the acceleration data of the train, and we transferred them to the load cases. And the load cases were used to understand how the part was actually behaving under these loads. So finite element modeling allowed us to see the benchmark. Then we took the part and we defined our constraints in terms of how many parts we want, the assembly joints and so on. And we use this design region in order to go for a topological optimization. Now, topological optimization is, it matches very nicely with laser powder bed fusion, but as you see, the optimization results are not really optimal for production. So we had to also go on with the design, do modifications, and the final design was once again tested in finite element modeling, allowing us to see that we maintain stiffness and reduced the weight quite significantly. Last but not least, the part was supposed to be also modified for manufacturability by laser powder bed fusion. We did some basic modifications in order to make the part producible as fast as possible. This is the digital image of the part that we designed, and this was manufactured in Milan at a certain part of the task. So putting everything together, original compared to AM, at least on a calculation basis, we saved 60% of weight. We reduced the part to be assembled from 17 to 2. From design to manufacturing, we reduced the time from several months to a few weeks. And essentially, we made a part that was better than the conventional one, at least in terms of how it was designed. So another achievement is that we designed a spare part for railways industry, which was topologically optimized. I'm going to go through some of these testing results rather quickly, because this was somehow exceeding our expectations during the project. So once the part was made, and maybe I should also mention that this was through the pandemic, and we also found out once again that the additive manufacturing adds resilience to logistics and manufacturing overall. So the part was made in Milan, it was sent to Rome for the heat treatment, and then it was sent to Madrid for the initial tests. So the initial test is assembly. We see that the antenna fits nicely, everything fits nicely. Then the static testing was applied by our colleagues in Madrid, pulling our antenna brackets statically in different directions. First of all, very humbly, we needed to see if anything broke. Nothing broke, which was very good. Then we gathered the data in terms of displacement, in terms of stiffness of the part, and we compared it with our calculations. And this was the validation of our part in a static way. The very nice thing about NextGear as a project is that the partners are very enthusiastic about what we have been doing. We didn't stop. Very recently, the part was also tested on track, which is an amazing opportunity for all of us. In Madrid, our colleagues mounted the new antenna bracket together with the conventional one. We gathered the vibration data on both of them, and we are still comparing these results for future communications coming out from this task. So, last but not least, this is just to show us where we started and where we came to. And the last achievement, I would say, that we were able to actually start from scratch, make a real railway spare part, calculate it and manufacture it by additive manufacturing and verify it. Thank you very much.
Really interesting piece of work there, and developed a real product that is now being tested and hopefully will start to be used. Okay, so the next section will be presented by Per Van Hagen. Per, if you're ready, Per is going to describe the composite frame which was manufactured. Thanks, Per.
KTH. Sorry, second one to do the mistake with the muting. My name is Per Van Hagen. I am an associate professor at the Royal Institute of Technology in Stockholm in lightweight structures. And I have been leading this subtask of the composite frame, and I will share with you some of the results from our side. So the partners in this subtask has been, apart from us, Huddersfield, RINA, Metro de Madrid, and Bercella. And Bercella is an Italian company, manufacturer of composite structures. So we started off with a target vehicle. You will hear a little bit more about this even in later on in this task, but we were aiming for a 2-axle vehicle with single-axle running gears of a novel design, and this included the active control systems as well. And our part was to design a composite part to replace a steel frame to keep the wheel set and the car body together. And you can see what it looked like. The final result is down here on the left. It's a fairly large composite part. You can see the axle box attachment at the bottom, and there are 4 points where we attach different spring elements to connect it to the car body. And then we have an actuator, which you will hear about more later on here. The whole idea was to see, can we use composite materials to improve the performance of this part? We used a type of carbon fiber material that is a so-called pre-preg. It's a pre-impregnated carbon fiber mixed with an epoxy resin. This is the highest quality type of composites that you can actually get. And we picked these very carefully so that these are composite materials that can fulfill the fire smoke and toxicity requirements as well. And we used different configurations of these in the design. We started with a very conceptual design phase. We wanted to do the most of the change of materials. We wanted to see if we could actually use the compliance and stiffness properties of the frame to work together with the suspension elements. And then, of course, we had to do a detailed design with all the little things that we need to take into account, such as load introduction and attachment points, and make sure that everything is structurally sound. The project also included a manufacturing of a full-scale prototype and testing of the same. So you can see some images here from the static strength analysis. We had to calculate the stresses in the composite layers to make sure that everything worked fine. Another important aspect was the actual deformation state of the frame. Here we had the intention that the frame could also take the role of an anti-roll bar to improve actually ride comfort in the vehicle. So quite a lot of simulations were also made together with the vehicle dynamics simulations, where we could actually see how the frame works together with the other suspension components to contribute to safety and comfort in the vehicle. After this, design was determined. We had a manufacturing plan. So this was done by Bercella in Italy, and it was a 3-stage process. This included a fairly large mold where the frame was first manufactured. So inside this blue is the shape of the frame, and carbon fiber layers are placed inside and cured. And then a number of metal inserts were used to introduce high loads for where the coil springs should be in these buckets, so to speak. And different other attachments. And the one on the left, on the right, far right here, the metallic part is for the introduction of fastening of the axle boxes. And the idea here is that all this metal part is embedded into the carbon fiber, but there are protruding elements that provide a metal-to-metal interface for bolting the axle box. So you can see here how thick the actual component is. The wall thickness is hollow, but the wall thickness is somewhere 10 to 15 millimeters, so it's quite thick. And this was also one of the reasons why it was manufactured in 3 steps. Right, the frame was shipped to our lab in Stockholm for testing. This is my colleague Anton, who did most of the analysis and the also major parts of the testing, which we did together. The final component weighs in at 76.5 kilograms, which makes it manageable for 2 people to carry around the lab and so on. It was quite nice. It was slightly above the calculated weight, which is not unusual for a first composite prototype, but within limits. We compensated for this in the models that we used to verify the structure. A test program was set up to see what to sort of verify the frame's properties. We wanted to characterize the structural flexibility and particularly the torsional stiffness of the frame, because we wanted it to be able to act as an anti-roll bar. So it shouldn't be super stiff, but at the same time, under other load conditions, it should be stiff. And we wanted to see if we had managed to do this with the design. We also wanted to see that all the finite element models that we had were sort of accurate or were modeling the right thing. And to verify that we could take the loads, we designed it to operational loads taken actually from standards for rail vehicles that are being used today. We also tested for the natural frequencies of the beam. This will give us an idea of the stiffness to mass ratio. And we did this before and after the static tests to see whether we could notice any stiffness degradation during the loading that we put on it. So this is what a setup can look like in the lab, not quite like the CAD drawing, but this is more reality. The frame is mounted upside down, so the orange-colored beam here represents the axle or the wheel set where the axle boxes are attached to the frame. We are using metal plates to distribute the load to these load introductions that I showed you. And the floor is sort of representing the car body with its attachment point. This is now more rigid than there are no springs. So we wanted to test the properties of the frame alone. So we measured the displacement at a lot of positions to make sure that we measure the right thing. But first of all, we made a model test to verify that we could calculate the natural frequencies with a finite element and see if this was corresponding to what the real frame had. And the results were really encouraging. We could see that at least, for these first modes, these results are really, really good. Say. And after that, the different tests commenced, and typically what the procedure was that we set up a test. This is for vertical testing. So we have a load point at the middle of the orange colored beam there that will press down with a hydraulic cylinder. And then we measure the displacement at a lot of different positions. And we pick out the same position in the finite element models where we actually make a finite element model of this particular test. In that way, we can get a fair comparison. There's a lot of measurement devices here that measure the displacement at different points so that we can subtract any rigid motions of the frame during the test. This was an initial vertical test to about 1/4 of the maximum load, and as you can see that the agreement is quite good. Then we did a twisting test where we loaded 1/4 of the frame and the other ones were restrained. This is to simulate the action as an anti-roll bar to see if we got the stiffness right. And again, the finite element model that we used was a model of the actual test, the way it looked here. And as you can see, the results are also really encouraging. It may be a slightly bit stiffer than anticipated, but not sort of way off. So we were very happy with this. The final test that we did was to load it in vertically to the design load. We did this last just to be sure that we didn't break anything, of course, before this. So we loaded it to a total load of 20 tons as if it was mounted on the vehicle, and this is the vertical compression case. You can sometimes hear when a composite structure is about to break that you can hear some cracking. And I didn't hear any cracking at all around this one. My hearing is quite good, actually, so I couldn't hear any cracking here. So what you see here is Anton, again, applying the load to the frame carefully, slowly. I'm standing in the background in a typical supervisor pose, surrounded by my PhD students. This is always an event in our lab when we test something big. On a completely different note on lightweighting, I said I probably lost 16 kilos since this picture was taken, and my weight is now the same as the composite frame, actually. Funny. You see the results here match the finite elements really well, almost all the way up. We had a little bit of a problem with an interference on one of the measurement devices here, so it deviates a little bit towards higher loads here, but this is not, we measured on both right and left side, and on the other side it looks really fine. And after this test, we did the modal testing again to see if the stiffness would have changed. We would have seen that, and there was absolutely no difference. The results were same. So the frame stood the test, and we are very, very happy with the results. With that, thank you for listening to this part, and I will hand over to the next part.
Hello, everybody. Can you hear me?
I'll try to stop sharing my screen.
Yes, Andrea, you're on live.
Okay, perfect. So I'm going to share my screen. Please inform me as soon as you see it.
Yeah, we see it.
Okay, perfect. Hello, everybody. My name is Andrea Del Sole. I'm the Innovation Manager at NEAT, an Italian SME that was leader in Task 2.2, the application of state-of-the-art technologies to railway landing gear. So the main activities, the slides are not moving, sorry, okay. The main activities foreseen within this task have been first, a systematic study aiming at identifying a small number of optimized control configuration for active running gear based on the result of previous works that have been conducted on this matter. And secondly, the development of another in-the-loop demonstrator of a control system for an active suspension system, including a novel actuator. In the systematic study we have conducted, that has been led by Professor Goodall from Huddersfield, we have identified several different control systems, among which we have selected with a sort of democratic but engineering and collaborative approach, two different models. The first one is the motorized independent rotating wheel set shown on the center top, and the actuated solid axle wheel set shown on the center bottom. We have also collected in this subtask, let's say, the system requirement to be applied in our project, among which we highlight here on the right the main ones that drove the, let's say, that drove the development of the controller. The first one is the frequency of the, let's say, of the sampling, computation, and actuation duty cycle that shall be up to 1 kHz for the motorized independent rotating wheel set model. And the second point is that alarm should be given by the control system in case of a failure, because the steering and the stability performances of the car body could be affected. And third, main important requirement is that in case of failure, the active system shall be deactivated. So the system shall go on in a safe state. And basically, there is a downgrade to the underlying passive independent rotating wheel set system of the car body. In this picture, the hardware in the loop C4 controller we have developed, we have set up in our project, coming from the requirement we had, is shown. We have selected among several different architectural and technical solutions a computer-based C4 controller based on leveraging on neat intellectual properties such as 2 out of 2 computing system hardware reference design and a C4 operating system. And this setup has been deployed at Huddersfield. In this moment, it's in Huddersfield where we are running tests. Another redundant system, so two different halves of the system, will be shown in the video that will be streamed during the break. This controller is composed by a 2 out of 2 safety computer shown on the left, based on a system on chip, diverse system on chip, and which is running the hard real-time operating system, and which is in charge of the safety integrity level, the high safety integrity level tasks, like in our case, the acquisition, computation, and evacuation. An ancillary communication computer running a dedicated Linux distribution in charge of the nozzle task, and of course the power supply unit. It's worth mentioning that a lot of tailoring has been done, especially on our operating system, in order to achieve the required 1 kilohertz, very challenging, by the way, duty cycle. This duty cycle, the best of our knowledge, is absolutely uncommon in railway applications. With the controller just shown, we have set up this test architecture. This is on the right. We can see the diagram showing the SIL4 controller on the right, and the external PC from which the test campaign, the test simulation are executed. The SIL4 controller acquires simulated stimuli from the external PC, compute the result according to the model, one of the 2 models we have tested in the project, and provide back to the external PC the commands, the actuation commands that should drive the actuators in a real context. On the mid-left, there is an exploit of the MATLAB Simulink and Dassault System SIMPAC real-time modules that we have used and are running on the external PC, where the car body module, which is the pictured above, is simulated in real time. This is the real setup. So we have the PC and on the left, the controller connected through an Ethernet port. And we have accessed this. We are accessing this setup remotely, so we can run different test campaigns from our premises or everywhere. The testing strategy we have followed is simply based on 3 different simulations to compare the vehicle dynamic results, given the track case of curve negotiation. So the truck is approaching the curve. In particular, we have compared 3 different systems: a passive one, so one with no control, an active one with the, let's say, the designed Simulink controller, and an active one with the hardware in the loop physical controller in the middle. And those are the results for the wheel set attack angle for the 3 different simulations. It can be seen that both wheel set of the passive vehicle system has very large attack angle during the curve negotiation, whereas the controlled leading wheel set in both cases has a much smaller attack angle compared with the passive one. The trailing wheel set without control has almost the same attack angle with the passive one. This slide instead show the result from the total wheel set wear index for the same 3 different simulations, let's say. The wear index of both wheel set of the passive vehicle system are very, very high, especially the leading wheel set identified as wheel set frame 1 in the picture, in the graph. This phenomena, together with the wheel set attack angle, reveal a very poor curving performance for the passive independent rotating wheel set system, which basically has no steering capacity. The wear of the controlled leading wheel set instead is significantly lower than the wear in the passive scenario, and the simulation shows that the wear index can be reduced up by 94%. In contrast, the uncontrolled trailing axle, so the wheel set 2, wheelset frame 2 has almost the same wear index with the passive vehicle. So this improvement in the vehicle dynamic performances of the controlled leading wheelset is quite significant according to our analysis. Therefore, we can conclude that the developed controller may implement the active steering function that was one of the goals of our project. At the end, we can, for concern the controller, we had also a graph of the active control torque among the two active systems. Let's now pass presenting the results for the actuator. So in the Run to Rail project that has preceded the NextGear, our NextGear project, a two-axle vehicle has been proposed as an alternative to the rolling stock which are currently used in Metro de Madrid. And this vehicle, despite having a great potential from the business point of view, has possible deficiencies for what concerns the ride comfort and the curving performances, which could be overcome, in our opinion, by introducing a wheelset steering actuators. And this is what we are talking about now. Here we are showing in this picture the basic steering principle. The goal here is to obtain a favorable angle for the wheel setting curves and thus reduce the wear. In general, not to control the stability. This is the actuator that has been designed, and it has been designed to have two different stiffness levels depending on the displacement in order to ensure the correct wheelset stability with a high longitudinal stiffness on one side, but also to reduce the active force needed to steer the wheel setting curves with a lower stiffness. Moreover, the actuator is equipped with a built-in springs to ensure a safe ride also in failure condition when the active part is not running in case. This is the test setup for the actuator. On top, there is the diagram, and on the left, the real setup in the laboratory. On the bottom, we can see the control diagram, which the principle of functioning with a single driving circuit. Let's come to the test results. The slides are blocked. Okay. So the actuator went through several different tests, and if not wrong, 8 different classes of tests, 7 or 8 different classes of tests. In this picture, for example, we are showing the result from the testing for the force versus displacement on the left diagram, and a good correspondence between let's say the ideal situation and the real one, the measured one, is shown. So there are deviations smaller than 15%, even smaller. So this result suggests that the fine tuning is necessary, but the results are quite good indeed. On the right, we are showing the result for the test of the force versus time at different driving current of the system. A sophisticated model has also been designed. Here is shown on the diagram on the left. Sorry, it's quite small, but it's complex, so it cannot fit into a single slide. But this model simulates the behavior of the actuator system. And it takes also into proper consideration the friction elements and the connection bushing. The graphs on the right compares the test results of displacement versus force at different frequencies for the simulated and the real system, and also the results of time versus force at different driving currents of the valves. We observe again, like in the previous graphs, a very good correspondence between simulation and measurements obtained during the tests. So this concludes the presentation of task 2.2, and now I leave the floor to Professor Ignitti for the conclusion of the work carried out in the whole work package.
Very much, Andrea. So I will just share my slides again. I only have 3 remaining slides, but I want to just draw some conclusions from our work package. Okay, hopefully you are seeing the slide pack again from me.
Yes.
So I think you've seen from the previous presenters that we've been very successful within this work package in developing, not just doing some really interesting development work, but also in actually producing, perhaps unusually for this type of project, 4 real physical prototypes, which we've then been able to test. They're just summarized here. I know there are a lot of words on the slide, but I just wanted to draw your attention to these 4 different areas. So we've optimized additive manufacturing processes and materials for the specific use that's is needed within a railway running gear. You've seen the bracket that Gorkan presented, really interesting, really exciting. When we took it to the to Metro Madrid, the technicians and colleagues there were really interested in it. And one of the advantages which was mentioned, but I just wanted to emphasize, but because of the lightweight, the reduction in mass, it doesn't only mean the things that conventionally come with reducing mass, but in this case, it changed the operation quite dramatically. The previous bracket required 2 people to lift it and to fit it in place, and to with the new bracket, 1 person could pick it up, and that potentially could mean another big advantage in the future. So, and that was great to see that being tested on the track. Then Per explained the carbon fiber composite frame, which is again a very novel concept. It's been designed and manufactured and tested, and the tests have shown good validation of of our predictions within the computer simulations. And potentially, I think this has big impact on the railway running gear for the future. Probably again, it shows the type of development where we can start to bring several components into one and take advantage of the material. Per explained that not only was this a frame to which the suspension components were fitted, it was lighter than the steel equivalent, but it also included, because of its flexibility, the role of a torsion bar, which would otherwise be required as a separate component. So I think these techniques have potential to reduce the number of components, and therefore we have to try to be able to reduce the initial cost as well as the life cycle cost. Then you saw Andrea presented the novel active damper. So this is a damper with 2 different stiffnesses and being an actuator as well. We've tested that in the laboratory. Colleagues within Delna have tested it, and that again shows huge potential. And Andrea, of course, explained the SIL4 controller, which is really new and really important. And without that, the rest of the running gear innovations really wouldn't work. And that's now being developed and tested and shown to be workable. So I think from that point of view, we have really good outcomes from our project. I wanted to mention dissemination, because as Jose and Javier mentioned at the beginning, this is very important. We're many researchers within the project. We're very keen to disseminate. We've already produced 3 journal papers which have been accepted, and participated in conferences where we presented our work to industry and other academic partners. We have 2 more papers in the pipeline which will be submitted to journals, so good dissemination from the project. But there are challenges as well, and as I mentioned at the beginning, we have to get these innovations accepted. Having the information from the life cycle costing and the business case, which colleagues are just finalizing now, will help, but we've suggested some next steps as well. So probably further testing will be needed on the antenna bracket. We took it out on the train on the test track, but it's not yet allowed. It doesn't have acceptance, product acceptance, vehicle acceptance. We need to do some more work with Metro Madrid and others so that it can be fitted to a vehicle and really used as a prototype, and then maybe as a product. For the single axle frame, Per described the static tests that were carried out. Probably the next thing we need to do there is to carry out some fatigue testing, again, so that this type of component can be used in the future on a real vehicle. So we're suggesting a number of continuations for the project, a couple of them mentioned here. We'd like to extend the in-lab evaluation, so to connect up some of the different elements, the NextGear controller, to some real sensors and actuators. Andrea explained how we tested it in the hardware in the loop environment, which is a good way of demonstrating that it's effective, but we have to still go into reality with it. And the novel actuators, it would be nice to fit 2 of those into a wheel axle, maybe even in with the composite frame, and then to apply more realistic disturbances and to study the stability and the behavior of the system. So I think there is more work to do after the project finishes to get acceptance and get the products really taken up. I just wanted to show you here back to this slide, so showing the structure of the project. We have delivered deliverables. These deliverables, some of the ones that have been more recently delivered are still awaiting approval from the JU, but once those are approved, they are all public deliverables, so we will use them to disseminate the work as widely as possible. We have the one final deliverable still to complete, will be completed by the end of the project. We have collected the data, and colleagues in RINA are now working on the lifecycle cost and the business case. And just a final comment from me, Javier mentioned at the beginning as well, when we started our work package, here we are on the left at my university in Huddersfield having our kickoff meeting. We didn't know that that was going to be the only time that we met face to face, and that all of the rest of our meetings would be using Teams and Zooms and all the other tools that we've become so familiar with. But I think we've managed very well despite that, and we've worked together as a team really well. And I want to thank my colleagues for working so effectively together, and for the support that Jose has given to us, and Sebastian as the technical and the overall project lead. So thank you very much. I will stop there. And Jose, I guess it's time for questions, if I'm right.
Yeah, thank you very much, Simon, for the presentation, also for Gökhan, Per, and Andrea. Okay, so you have realized what I mentioned at the beginning, the impressive results that we have of this project, and as mentioned by Simon, that it deserves a continuation for sure. Okay, so regarding the questions, let me check. We have received 2 anonymous questions, so they are a bit shy to say who asked this question, but okay, in any case, the first one I think is for Gökhan. It said, there is a change in the material, steel to aluminum. What would be the mass gain with only a change in the material?
So that's actually quite straightforward. Nice question. We achieved 60% mass reduction by means of material and design combined. So, of course, the mechanical properties of steel and aluminum are definitely different. So we couldn't just take the same design and change the material and benefit from the density difference, and that would have reduced the weight differently, but essentially the mechanical behavior would have been much more different. So this is why the consideration of weight reduction has to take into account the conditions when you can fulfill the mechanical requirements by means of the two combinations that I said before. So essentially the same geometry, just by changing the material, would have reduced, if you just take into account the density, would have reduced about, once again, 70%, I would say, the weight. But then you wouldn't have the same mechanical behavior. So aluminum doesn't have the same stiffness, it doesn't have the same yield strength, and so on. The nice thing about digitalized manufacturing is that you calculate the geometry that is required, that passes through the design space. So as a matter of fact, we reduced density, but we also reduced the mechanical properties, but we put the material where it was required. So we came to the conclusion that we could reduce the weight by 60%. So I hope this is good enough just to say that you can't really take the same geometry and change the material and say, use it this way. there are also implications related to the manufacturing cycle, because the same geometry with aluminum alloys, you can't really get the same manufacturing cycle. The welding is also different and so on. But it is actually quite striking that I didn't really underline the details of, at least on a calculation base, what we achieved. By combining the geometry, which is very important, geometry is very important, with a lightweight material, not only we reduced the weight, but it's actually a safer component in terms of safety factor. So the minimum safety factor was also increased. And the maximum displacement, at least on a calculation basis, it was still not exceeding the original component. So once again, I understand the question quite well, because aluminium as an alloy it's a rather new material for the railway industry. It's not very well used, very widely used. But to give you an idea, we jumped into the combination also coming from run to rail experience, because we also studied similar alloys in the past as a concept. And we figured out that in order to reduce weight and in order to make benefit of all the geometry, it was a straightforward approach to go for aluminum alloys in that case.
Okay, thank you very much, Gökhan, for your reply. As you can see, we are not only good with the results, also with the explanation. Thank you very much, Gökhan. It has been really clear.
Thank you very much.
Okay, so we have another question for the slide 42-45. Okay, I don't really know what are this slide, but okay, the question is, was the wheel set axle recalculated? The steering system seems to introduce forces up to 40 kilonewton to the axle. I think it's related to the actuator, if I'm not wrong, but Simon, can you check? You are muted, Andrea.
The slide, would that be helpful? Then I don't know if it's Andrea or me can answer.
I don't know if I can answer, but I can share the slides for sure.
Okay, thanks. Yeah, share the slide then.
Let me go full screen. Go on 45. So
45 is showing the results.
Exactly.
With the hysteresis, is that the one?
So share the screen.
It's a slide 42-45. This is what.
Oh, 42 to 45. Okay.
Yeah.
Okay.
Yeah. So 42 shows the setup.
Yeah.
And well, sorry, can you just repeat the bit of the question?
Yeah. The question is.
It's about the forces.
Was the wheel set axle recalculated?
Recalculated.
The steering system seems to introduce forces up to 40 kilonewtons to the axle. Okay, regarding this question, because the expert in the actuator is not Andreas, so I think that could be good to address this question later, or how?
Yeah, maybe if I can just say a few words. I don't think any of the other colleagues can join the talk, can they? So yes, the idea of the actuator is that it can steer the wheel set. You see it here in slide 42, where the actuator either side can, by pushing on one and pulling the other, can steer the wheel set into a good position for the curving. So you can kind of balance the forces, and at the same time the vehicle is stable. There's always this conflict between steering and stability in the design of the running gear. But the question seems to be about the maximum forces, which I'm sorry, I don't quite understand the point of the question. Maybe it's questioning whether the actuator can apply enough force, or whether we tested it to a high enough force in the testing. Yeah, it's probably referring to the graph on slide 45, isn't it? Where the force is going up to 45 kilonewtons in each direction.
Yeah.
My feeling is that's enough force, but I'm sorry, I don't quite understand the question. Perhaps can we take that offline if?
Yeah, I think it's better. In any case, there are no more questions. So okay. The point is, for this question and any others that could be raised afterwards, okay, don't hesitate to contact us. You have my contact details in our website. So send me an email and I will address these questions to the proper expert. Okay.
Thank you.
Okay, so no more question. Okay, again, really thank you to all Work Package 2 partners, because it is really impressive the work that you have done. And okay, I hope that we'll have the opportunity to work again in the future. So now it's time for the break after 2 hours. Okay, although I had some concerns at the beginning of the conference call that we will be on the schedule, it is true. So really good work done also for all of you. So okay, we can have a short break of 10 minutes, let's say, and you will be able to watch the video that we have prepared for the results of the project. I don't know, Simon, do you want to say something?
No, just to say thank you very much again to all partners, and thank you also to you, Jose, for your support. And I think this work package has been very successful. I really hope that all of these results will be taken forward.
Mm-hmm.
Thank you.
Okay.
Can we all see the video, Jose? Will it be shown now?
Yeah. Okay, so we will continue in 10 minutes.
Thank you very much.
A new generation of running gear is very important to achieve the ambitious goals set up by Shift2Rail for future European rail vehicles. This includes significantly reduced life cycle costs, improved reliability and energy efficiency, and also reduced vibrations and noise emissions. NextGear therefore develops a variety of innovations for future running gear.
The reduction of the mass of the wheel set is related to the importance of reducing the mass of all the parts coming into contact with the track. This helps to reduce the damage of the rolling stock of the rails and also reduce the noise and the vibration coming from the vehicle. So in Work Package 3, we developed a technology concept of a hybrid metal composite axle. And the weight reduction we achieved for the axle was 60%, and the overall mass reduction for the wheel set was 14%. To develop this hybrid composite metal axle, we had to face a lot of challenges. First of all, we had to design the structure, we had to optimize the fiber layup, and then we had to study the connection with the metal parts and the connection with the bearings, the wheels, the position of the brakes. Then we had to consider feasible ways of inspecting this complex part and also ways to perform structural hand monitoring of the part.
There's huge potential from using new materials and new components and new methods of operating these components. And in particular, in Work Package 2, we've been investigating two potential improvements. One is the use of fiber reinforced plastic to make a lightweight frame within the bogie of the vehicle, and the other one is use of additive manufacturing methods, where we make a novel component which is lighter and more robust and potentially more reliable than the existing components. We are also developing a high safety integrity level controller. This controller is necessary so that we can control the different active components which we have in the suspension. Using active components allows us to improve the performance of the suspension, for example, by reducing the damage on the track and reducing the energy consumption of the vehicle.
A challenge in using composite materials in running gear is to prove that they can fulfill all the requirements on lightweight vehicle components. This has been addressed in Work Package 2 through the conceptualization and design of a lightweight carbon fiber frame, which was tested here in the Lightweight Structures Laboratory at the Royal Institute of Technology. The work has demonstrated that carbon fiber composites can be used as part of a novel running gear. We achieved significantly reduced mass and better or similar performance to a conventional running gear.
Metal additive manufacturing can provide several benefits to the railway industry. we're working with metallic powders and automated machines to make parts in a layer-by-layer fashion. So in NextGear, we concentrated our efforts especially in order to understand how we could change the manufacturing of spare parts, especially where required and when required, using digital files. So we collaborated with Metro de Madrid, and we redesigned their part using railway data, real railway data. And the component was manufactured here in Milan and tested on the track in Madrid. So we achieved a 60% weight reduction of the component. We were able to put the component from 18 parts down to 2. And we were able to manufacture it in less than 2 weeks compared to a few months in the conventional case. So this was a quite nice way of showing the railway industry the benefits of metal additive manufacturing, which we hope will be used more often in the upcoming years.
The use of active elements may lead to a better trim of the car body approaching the curves by reducing the centripetal acceleration and thus reducing the wear of both wheels and tracks. Moreover, the suspension system, both sensors and actuators, can be monitored to check the efficiency and detect anomalies in their behavior. In the project, we set up a hardware-in-the-loop SIL4 controller with simulated sensors and actuators running at 1 kHz. A future improvement could be introducing dedicated I/O boards interfacing real sensors and actuators.
The universal cost model is a simulation framework that enables to compare life cycle costs of different running gear types, especially their impact in different railway system stakeholders. The UCM allows to check for pros and cons of novel, innovative running gears at the system level. The UCM does not simulate directly the innovations, but what it does is simulates the impact of those innovations in different cost-generating concepts. What it means is that for the NextGear project, we could not model all the innovations, and what we have done is to explain and break down the process and how a new innovation should be implemented in the UCM in order to be able to calculate their benefits and their pros and their cons. The main challenge is to achieve the right balance between accuracy and user-friendliness, because different stakeholders will have different expertise levels in these simulation techniques and then different expectations of what a good level of accuracy and usability should be.
Additive manufacturing and bogie frames and wheel sets based on carbon fiber materials can significantly reduce the weight of future running gear. The controller and the innovative actuator that we developed in the project show the performance of active suspension in rail vehicles. That will improve the performance and enable new vehicle concepts. The positive impact on the life cycle costs can be verified with the universal cost model that is also developed in the project. A new generation of running gear is very important to achieve the ambitious goals set up by Shift2Rail for future European rail vehicles. This includes significantly reduced life cycle costs, improved reliability and energy efficiency, and also reduced vibrations and noise emissions. NextGear therefore develops a variety of innovations for future running gear.
The reduction of the mass of the wheel set is related to the importance of reducing the mass of all the parts coming into contact with the track. This helps to reduce the damage of the rolling stock of the rails and also reduce the noise and the vibration coming from the vehicle. So in Work Package 3, we developed a technology concept of hybrid metal composite axle. And the weight reduction we achieved for the axle was 60%, and the overall mass reduction for the wheel set was 14%. To develop this hybrid composite metal axle, we had to face a lot of challenges. First of all, we had to design the structure, we had to optimize the fiber layup, but then we had to study the connection with the metal parts, and the connection with the bearings, the wheels, the position of the brakes. Then we had to consider feasible ways of inspecting these complex parts and also ways to perform structural hand monitoring of the parts.
There's huge potential from using new materials and new components and new methods of operating these components. And in particular, in Work Package 2, we've been investigating two potential improvements. One is the use of fiber-reinforced plastic to make a lightweight frame within the bogie of the vehicle. And the other one is use of additive manufacturing methods, where we make a novel component which is lighter and more robust and potentially more reliable than the existing components. We are also developing a high safety integrity level controller. This controller is necessary so that we can control the different active components which we have in the suspension. Using active components allows us to improve the performance of the suspension, for example, by reducing the damage on the track and reducing the energy consumption of the vehicle.
A challenge in using composite materials in running gear is to prove that they can fulfill all the requirements on lightweight vehicle components. This has been addressed in Work Package 2 through the conceptualization and design of a lightweight carbon fiber frame, which was tested here in the Lightweight Structures Laboratory at the Royal Institute of Technology. The work has demonstrated that carbon fiber composites can be used as part of a novel running gear. We achieved significantly reduced mass and better or similar performance to a conventional running gear.
Metal additive manufacturing can provide several benefits to the railway industry. We're working with metallic powders and automated machines to make parts in a layer-by-layer fashion. So in NextGear, we concentrated our efforts especially in order to understand how we could change the manufacturing of spare parts, especially where required and when required using digital files. So we collaborated with Metro de Madrid and we redesigned their part using railway data, real railway data. And the component was manufactured here in Milan and tested on the track in Madrid. So we achieved a 60% weight reduction of the component. We were able to put the component from 18 parts down to 2. And we were able to manufacture it in less than 2 weeks compared to a few months in the conventional case. So this was a quite nice way of showing the railway industry the benefits of metal additive manufacturing, which we hope will be used more often in the upcoming years.
The use of active elements may lead to a better trim of the car body approaching the curves by reducing the centripetal acceleration and thus reducing the wear of both wheels and tracks. Moreover, the suspension system, both sensors and actuators, can be monitored to check the efficiency and detect anomalies in their behavior. In the project, we set up a hardware-in-the-loop Steel 4 controller with simulated sensors and actuators running at 1 kHz. A future improvement could be introducing dedicated I/O boards interfacing real sensors and actuators.
The universal cost model is a simulation framework that enables to compare life cycle costs of different running gear types, especially their impact in different railway system stakeholders. The UCM allows to check for pros and cons of novel, innovative running gears at the system level. The UCM does not simulate directly the innovations, but what it does is simulates the impact of those innovations in different cost-generating concepts. What it means is that for the NextGear project, we could not model all the innovations, and what we have done is to explain and break down the process and how a new innovation should be implemented in the UCM in order to be able to calculate their benefits and their pros and their cons. The main challenge is to achieve the right balance between accuracy and user-friendliness, because different stakeholders will have different expertise levels in these simulation techniques and then different expectations of what a good level of accuracy and usability should be.
Additive manufacturing and bogie frames and wheel sets based on carbon fiber materials can significantly reduce the weight of future running gear. The controller and the innovative actuator that we developed in the project show the performance of active suspension in rail vehicles. That will improve the performance and enable new vehicle concepts. The positive impact on the life cycle costs can be verified with the universal cost model that is also developed in the project.
Okay, so welcome back to the event. I hope that you had enough time to take a refreshment, some coffee, to recover your strength, your breath, because we have transmitted a lot of information, and I think that you need some time to digest it. So I hope that you recover this energy and strength to continue with the second part of this session, and also you enjoyed the video. So now it's time to come to the wheelset of the future. So Stefano Bruni is going to present this topic, how the composite material can contribute to it, and essentially in one very, very important part, that is the axle of the wheelset. So Stefano, please, the floor is yours.
Thank you, Jose. So I will assume you hear my voice, and I'm going to share my screen. So I hope you also see my screen. So yes, first of all, good morning to everyone. And we already talked earlier this morning about reducing the mass of different components in the vehicle. It is particularly relevant to reduce the mass of so-called unsprung masses, so the bodies coming directly in contact with the track, because these bodies are especially relevant to damage in the track, like in the rails for rolling contact fatigue and wear, but also in the track in a more general sense, producing damage in different track components, fasteners, sleepers, and also degradation of geometry for the line. So WP3 addressed the wheelset of the future, which is an attempt or an evaluation of the possible use of composite material, lighter materials for the wheelset. And as we will see, we focused especially on the wheelset axle. It is, compared to work package 2, this work package has a slightly lower TRL, so we were not really looking into building and testing prototypes. We were rather looking into elaborating technology concepts and assessing them in terms of simulations and modeling. So this slide resumes some main points in the work package. The scope, as I said, was to perform a feasibility study for the use of composite materials in the construction of railway wheelset. Politecnico di Milano was the leader for this. I am actually working at Politecnico di Milano. The other partners involved were KTH, Lucchini, RINA, University of Leeds, University di Nebrija, Metro de Madrid, University of Nottingham, and Burchella. Burchella is an Italian small, medium-sized company designing and producing composite components for different, let's say, applications, including automotive, aerospace, and very interested into entering into the railway market. The outcome of this work package is a technology concept for a hybrid metal composite railway axle, as we will see. First of all, I would like to present shortly the case study. So we wanted to consider a real case. So we selected out of different possible cases, the one which is shown in this slide. It is based on a product from Lucchini. It is the axle for an inboard bearing trailer wheelset, as you see here. And in this wheelset, the disc brakes are mounted on the wheels, which we thought was a nice starting point for our work, because in this case, you have no need for an interface of the axle to the discs, which was simplifying the interface part of the work. And of course, composite to metal interfaces are a critical, let's say, point in designing a wheel set, including composite parts. The mass of this component is nearly 200 kilograms. So this is the reference mass. We'll see later on to which extent it was possible to reduce this mass by the use of composite materials. I would also like to notice that, of course, the benefit we are getting by replacing the steel axle by a composite axle, in this case, where we have inboard bearing, is a little bit lower than in a different case with the outboard bearings, because in that case, the axle would be longer and it would involve a higher mass. So this slide, the first part of our work was concerned with defining possible concepts for an axle partly made of composite material. And in the end of this first part of the work, we came up with the 3 different concepts. We called concept 1, concept 2, and concept 3. You see the 3 concepts in this slide. The idea was that concept 1 was the most optimized in terms of allowing the designer the highest degree of freedom in terms of how the composite fibers should be laid in the axle. So this is a wound tube. We have a small inner metallic part, which is the light blue part you see here, and then the composite fibers are wound over this support, let's say. The interface to the bearings and to the wheels is provided by 2 metallic stub axles, which you see in the outer part of the axle. So this part is still made out of metallic material, steel, and just the central part of the axle is made out of composite. This is one of the reasons why this concept 1 was leading to a modest mass reduction. We estimated the mass to be 190 kilograms compared to the 200 kilograms for the steel axle, so not such an important mass reduction. So this concept was abandoned quite soon. Concept 2 was meant to provide the lowest manufacturing cost for the axle. It's called a pre-manufactured tube. So the idea was that the composite tube realizing the central part of the axle could be pre-manufactured in long pieces and then cut to sides and joined to, again, 2 stub axles, metallic stub axles in the external part of the axle. This was, of course, optimizing, as I said, the manufacturing cost, but again, it was providing not so large a reduction of the mass. Around 1/4 of the mass of the steel axle could be, let's say, eliminated, so leading to a mass of approximately 150 kilograms compared to 200 for the steel axle. And again, this was mainly due to the fact that we still have a significant length in this axle, which is made out of steel. So the third concept we came up with is the so-called full-length tube. And this was meant to minimize the mass of the axle, despite the manufacturing cost is higher than for concept 2. In this case, we have, as the name says, a tube made of composite, which is running throughout the entire length of the axle. And we just have metallic collars, so quite thin metallic collars, covering the tube at the interfaces with the wheels and the bearings, which of course reduces quite substantially the mass of the axle. And in this case, we could bring down the mass of this hybrid metal composite axle to 80 kilograms, so with a 60% reduction compared to the steel axle. This slide provides some more details about how this concept is done. We have as I said, a continuous composite tube whose length is the same as the axle, as the full axle. And we have thin-walled metallic collars at two extremities, providing, as I said, the interface to the wheels and the bearings. Adhesive bonding, so gluing, is used to connect the metallic collars to the inner tube. And while developing this concept, we realized that we were in need of what we call a secondary composite tube, so an external tube, which overlaps to the primary full-length tube in the central part of the axle. And this was required to meet flexibility requirements or stiffness requirements for axle bending. As I already said, the mass reduction compared to the benchmark steel axle is 80 kilograms compared to 198, so 60% mass reduction. Of course, the total mass reduction for the complete wheel set is lower in percentage terms because we are not changing the wheels and bearings, so the weight of those parts remains the same. Still, we could achieve a 12% reduction for the overall mass of the wheel set, which is still very significant. And this picture shows how the complete concepts for the wheel set with the hybrid metal composite axle, this acronym HMC stands for hybrid metal composite, looks like. So you see the composite tubes and the collars providing the bearing seats and the seats for the press fitting of the wheels, and then the wheels, and you see the disc brakes are not shown, but you see where they would fit into the wheels. So this was the first part of our work, and then of course we wanted to analyze this concept and to analyze its feasibility by looking into different areas. The first one was a detailed structural design of the axle and an optimization of the layup. Then we had to look into a proper solution for the bonded joint joining the metallic collars to the composite part of the axle. We had to investigate the manufacturing process and make sure that there is a suitable manufacturing process that can be used to produce this component, and also get, let's say, an initial estimate of the manufacturing costs. One very important point was about non-destructive testing and structural health monitoring to check the structural integrity of the axle. Of course, this is a safety relevant component. So even for steel axles already in service, there are very stringent requirements about inspections, about checking that the integrity of the axle throughout the life of the axle. And clearly the use of a totally different type of material impacts very significantly on these issues. So we wanted also to show that there are ways to perform a suitable inspection of the axle that will ensure the safe operation of the axle throughout its life. As part of that, we also needed to consider the impact with ballast stones or with other objects, which is possible for axles. And for steel axles, this may cause the initiation of a fatigue crack. For a composite, for an axle made out of composite materials, this can cause different types of problems. So we wanted to investigate these problems as well. And then, of course, we wanted to evaluate the effect of the lighter axle on running dynamics and vibration. So going into a demonstration of the benefits of the lighter axle. And finally, we envisaged an assessment of the life cycle cost. And in this area of our work, we agreed with Work Package 1 that this composite axle would be one example for the application of the Universal Cost Model 2.0. So I will not really present so much of this work in my presentation, but I will leave to Carlos to show some results. Going a little bit more in the detail of the structure design and optimization, we came up with a detailed design for the steel collars. The philosophy here is to let the steel collar to take all radial and circumferential stresses which are related to the press fit of the wheels and bearings, and let's say leave to the composite only the role to bear the bending stresses and to realize the required bending stiffness. We don't have much torsional stresses in this case because this is a trade wheel set, and at the same time these brakes are mounted on the wheels, so there is not much torsion being transmitted through the axle. One important point was about making sure that the hybrid metal composite axle could meet, let's say, flexibility or stiffness, bending stiffness targets, for which we used the steel axle as a reference. And that was the part of our work where we realized that by just using the inner full-length composite tube, we would end up with possibly too flexible axle. It may be a subject for further investigation whether one could accept this higher flexibility as long as it is not impacting, of course, on the structural resistance of the material. Here, the problem was not really with the maximum stresses exceeding the limits, but rather with the maximum bend deformation exceeding some limits that we decided internally in our work. Nevertheless, we could solve this issue by adding a secondary composite tube and by, let's say, optimizing the layup of the primary inner tube and secondary outer tube in terms of the number of plies, thickness of the plies, and so on. And this led us to a final, let's say, frozen design for the complete hybrid metal composite axle, which is summarized in this image, where you see basically the directions of the fibers, the thickness of the different components, and the main geometric properties. In terms of the joining of the metallic collars to the primary and secondary tube, this was another very important and time-consuming part of our work because this is totally new, and of course we wanted to design a solution which is completely compatible with the stresses that need to be exchanged between the metallic and non-metallic parts in the axle. So this was done by means of finite element models and finite element analysis. We found that it is particularly critical to ensure a smooth transition where, let's say, the metallic collar transitions into the into the part of the axle which is only made of composite material. You will see that here the adhesive bonding layer is represented by a blue line, which connects, let's say, the metallic collar to the inner tube and then folds back into providing also a connection between the secondary composite tube and the outer part of the metallic collar. So with this solution, we ended up with finding a very nice stress distribution in the adhesive material and a solution that would, at least from the point of view of detailed finite element analysis, provide a very safe and durable connection of the metal part to the composite parts of the axle. In terms of non-destructive inspection of the axle integrity, well, we performed a lot of work. I don't have time to go into very fine details about that, but I will just say that we used a specific software to simulate the ultrasound inspection process for this axle. So basically, we simulated the propagation of ultrasound waves inside the axle to see how the axle would react to, the ultrasound method would react to the presence of a defect in either the composite or the metallic part of the axle. We found that as long as we look into the central part of the axle, where we have the joining of the inner and outer tubes, which are both made of the same material, the composite material, then, as you see from this image, you see here the circular probe used for the ultrasound inspection. And this map shows how the ultrasound waves propagate into the material. And you see we have a nice transfer of the ultrasound waves from the inner tube to the outer tube, which means basically the entire thickness of the axle can be properly inspected, effectively inspected. When we get into the part, into the lateral region of the axle, the portion where we have the outer metallic collars, then we have an important mismatch between the acoustic impedance in the material of the inner portion, the composite tube, and the outer portion, the steel collar. And this basically blocks the ultrasound waves, which means any defect which could be in the outer part could not be seen by this inspection method. So we devised different methods which can be based on the on disconnecting, let's say, the wheels and bearings and inspecting the collars from the outside, or using some continuous structural health monitoring methods, which could complement non-destructive inspections in a way that may ensure that any possible potential damage in the axle is timely discovered and treated properly, let's say. As part of that, we also analyzed the effect of impacts from ballast stones. This was done using, again, finite element simulations, explicit simulations, considering a spherical projectile impacting the axle in the center. And we considered different conditions, like in particular for the angle of the impact. And we used the Hashing failure criterion, which is commonly used for composite materials, to quantify the damage caused by the impact. We found that in both cases, impact only occurs in a relatively limited region of the outer tube, which is probably not so, let's say, dangerous in terms of the damage created initially, but of course you get some local damage that could evolve later on in more serious damage requiring some maintenance action. We also considered the use of different external layers to protect the outer tube, composite tube, and we found that this would be certainly desirable. This is a solution that Lucchini, sorry, is already adopting in some cases for steel axle, like non-metallic covering layer, which is protecting from impacts of the outer surface of the axle. And so this could also be of interest in case a composite axle like this one could be brought into service. Another part of the work was related to the manufacturing process. Here there are basically two manufacturing process methods that can be envisaged for this application. One is roll wrapping. So have a sort of pre-impregnated fiber, which is wrapped over a mandrel to produce the tube, which is then cured and treated to produce the final composite part in the axle. The other manufacturing method is filament winding. So by means of, let's say, kind of automation process or robotic system, filaments of carbon fibers are wound over a mandrel, and then the external parts are cut, producing the tube. The benefit or the nice point with roll wrapping is that because the stresses in the composite tube are mainly due to bending, then roll wrapping allows to align the fibers in the axial direction for the tube, which means there is a chance to maximize the stiffness over mass ratio. So you get the highest stiffness for a given mass of the tube, I mean bending stiffness. In filament winding, as you see from this sketch, it is clear that you cannot directly align the fibers axially, because then you could not wrap them around the mandrel. So you need to have some kind of angle for the wrapping, and this leads to a slightly reduced ratio of stiffness versus mass. But the benefit, the nice point with filament winding is that this is a process that can be made totally automatic. So it means the costs, the manufacturing costs are lower because there is less human intervention, let's say, or less use of human operators in the manufacturing process. And also the final quality of the project is subject to lower variability in that. I mean, it's fully automated, so there is no effect of human intervention on this. So our work was to find out what could be the best filament winding process, which would provide, say, a bending stiffness that was very close to the roll wrapping solution, yet enabling the use of this filament winding manufacturing process. And this was done by a combination of optimization methods with HyperWorks, simulation of the winding process by a specific software CAD window, and finite element simulations. I think I'm a little bit running short of time, so we'll try to speed up, but there are not so many slides remaining in my presentation. The evaluation of the effect on vehicle running dynamics was done by means of simulations performed in software Simpac. So we built a model for a metro vehicle and included the new wheelset with a hybrid metal composite axle and compared this to the reference steel axle. In this sample result, you see in orange and blue the results we get in terms of the variations of the vertical wheel rail contact force at the four wheels in one bogie. In orange, the result for the new wheelset with the lighter axle, and in blue, the result for the wheelset with reference steel axle. So you can visually see that there is a significant reduction of the maximum dynamic vertical forces. And this is, of course, more relevant when the speed of the vehicle is relatively high. So we went up to a maximum speed of 90 kilometers per hour. We also had a vibroacoustic analysis looking into how the natural frequencies and modal shapes of the wheelset are affected by the new lighter axle. And we used train track interaction models to see the effect of this. And we could see that the wheelset with a hybrid axle provides a reduction of the dynamic normal force in a frequency range from 30 to 70 hertz, which is really highly relevant for the transmission of ground vibration. So we expect less vibration and noise emitted by a vehicle which is equipped with this new type of wheelset instead of a conventional wheelset. In terms of estimation of the life cycle costs, as I said, we left this part of the work to Work Package 1, but we provided Work Package 1 with all the inputs that were needed for this. We had an estimate of the production cost. As you see, it is split into two cases for filament winding and for roll wrapping, and you see that roll wrapping leads to a significant higher cost. We also had an estimate for the initial cost of the steel axle. Of course, there is a difference. The initial cost, this is clearly unavoidable, but still it's not, let's say, a tremendous difference. And we also had a complete evaluation of the difference and the impact on the maintenance costs on a yearly basis. Just want to mention very quickly that we also had a demonstration phase, which was not initially foreseen as part of the project, but we were able to produce some scaled 1-in-5 specimens of the composite axles and test them on a single wheelset, as you see here, and then on a scaled roller rig, which is available at Huddersfield University. So to show that actually the concept is feasible. I was thinking of saying a few words about standardization issues, but I see the time I have available is coming to an end. So maybe I will skip this slide and I will leave in case for questions any issue regarding standardizations. I would just like to conclude with disseminations. We also had a very nice dissemination of our activities. So we have already 2 journal papers published on composite structures and one on the Journal of Rail and Rapid Transit. We have 1 paper finally accepted just in the production pipeline on applied sciences and engineering progress. We have 1 abstract submitted to WCRR 2022 in Birmingham, which we hope will be accepted. And we have another paper already submitted and 1 paper in preparation. So I think this is my last slide. So I thank you for listening and I hope I can raise a
Okay, so thank you very much, Stefano, and also for managing the time. So yeah, in order to leave time for questions, although checking the chat, I don't see any question really. So I would like to thank not only to you, all the participants in this work package, because it has been also really challenging and you have done a really great job for sure. Just to highlight the importance of this reduction of the mass that can contribute, as Philippe mentioned at the beginning of this conference call, to the Green Deal that the European Union is pursuing. So we will have less consumption and also we will reduce the footprint, the carbon footprint. So it is really good to follow this activity for sure. Okay, so thank you very much. If there are no questions, yeah, I have been informed that no question. So we can continue with the next presentation. And now, once we have reviewed all the innovations that we have achieved in the project, it is time to evaluate the benefits of this innovation. So for this, Carlos and the Work Package 1 team will present today the results. But it's important to mention, as I said at the beginning, that this tool was started in roll-to-rail, but in this project, KTH with the rest of the partner progress on it, upgrade the different modules, technical modules, also economic modules, and for sure the user friendliness of the tool. That this is also really relevant for the tool. So then, please, Carlos, can you let us know how you did it?
Yes, I can do that. Thanks for the kind introduction, Jose. I am sharing my screen. I hope you can see it. Yes, okay. So I have a laser pointer, but I will try not to use it that much. So yes, thank you for hanging in there. This is the third big section of the presentations today, where we will be presenting the, as Jose already said, the so-called Universal Cost Model 2.0. My name is Carlos Casanueva, and my pronouns are he and him, and I will be presenting first the overall perspective on this work package and its different tasks and work done. But we have also reserved time for a deep dive in two different specific topics that are particularly interesting in this context. One of them is switches and crossings, and for that, Jan Bessin will be coming in and presenting about how they modeled and implemented it. And then Andrew Smith from Leeds will have a deeper discussion comparing cost calculation methodologies. So now, what is the UCM or what are in general cost model tools, right? It's basically something that allows you to calculate the cost in a systemic way, or the system costs of something. You should be able, with a tool like this, to be able to quantify the differences on the impact of different changes in that system. So if you innovate and you have an innovative vehicle, you will definitely have different initial costs, different operational costs, and different end-of-life costs. And that is rather simple in a way, except that those costs sometimes come to different stakeholders in the railway system. So an innovation is paid by one stakeholder, can be paid by one stakeholder, but the impact is in different stakeholders. An example here is energy consumption or vehicle maintenance are usually costs assigned to operators, while infrastructure damage is a cost taken by the infrastructure managers, and noise and pollution are externalities or societal costs. So these innovative vehicle benefits, one has to be able to evaluate these costs in a good way in order to be able to justify these changes. Now, exactly the UCM, the Universal Cost Model, it was a methodology that was developed in Roll-to-Rail, and it is intended for, as we said, evaluating how a discrete improvement or change in the running gear impacts the life cycle costs of the whole railway system. There are two parts to it. One is the methodology, and the other one is the tool. The methodology covers the methods that you need to use in order to simulate the performance inputs. And the tool is how you transform those cost-generating inputs into actual costs. The general impressions from this project, or the feedback after Roll-to-Rail was finished, was that it was not a simple tool. There were some technical challenges, and there's a lot of information that was necessary for different people to be able to use it. So then, this is how it usually looks like. The methodology is a set of rules and guidelines for simulations, and the tool is some Excel file. It was an Excel file. It still is an Excel file, and the interaction between those two is basically that there are some inputs to the simulations. The user should simulate some variables that are called performance inputs. And those performance inputs will be introduced in the tool in order to get a final set of costs. This is how we organized the work package. We had 6 tasks, sorry. One initial literature review, especially for those that were not, those partners that were not familiar with the UCM. Then we had one specific task for infrastructure module development. Another one that bundled noise and energy modules. A third one that was about the vehicle modules, maintenance specifically. And those are, all of them are part of these rules, guidelines for simulations, right? And then regarding the tool itself and how to transform those performance inputs into costs, we had one task on cost methodologies and another one on the actual UCM development and the cases that were studied within. There were 3 deliverables, 2 of them in the technical part and a third one in the overarching model and so on. We needed an expertise in different topics. So you can see here the different partners that participated in this work, because we basically needed people that knew about every single part of the railway system. So it was a rather good collaboration between us. And one of the most interesting things that we did is that we had to do some interviews, specifically to pivot two partners, to understand what their opinion of the UCM is, to understand what their expectations are. So we created some presentation with the existing UCM at the time, not explaining it, showing the sharing the UCM and simulation guidelines, and we sent a written questionnaire also for them to answer us. And then we took that questionnaire and went into an interview, asking more specific questions about their answers in order to understand what their needs and expectations were. And we basically bundled, or eventually could post-process all those interviews and bundle and get some themes that are related, like trust and acceptance. Different users will be using the UCM, so they should trust each other. There is also an overarching thing about, or a tangent thing to that, right, which is like comparability, standardization, transparency of those calculations, and so on. And a lot of focus was also on the interface and layers. There are lots of keywords in the expectations, but a lot of the weight was put in the interface and the different layering of how we analyze the different parts of the different subsystems. And eventually what we did is to try to conceptualize all that in one concept design, right, or conceptual representation of what the UCM should be. And if COVID was but for something, it was for like doing brainstorming workshops. We had to do this digitally with all the partners involved, and it was not easy. But we eventually came up with this kind of conceptual design of the universal cost model, where we basically get the different things that the partners were asking systematically and try to implement those in a sketch way, right? So there are some main things here that I would like to highlight. One of them is that the complexity of the modules was something that was addressed quite early, meaning that some people would be able to do stuff in a more complex level or not. So what we did is what we created as a way of adding the complexity vertically, in a way that whenever one opens one of these modules for analyzing one of the subsystems, it can be used as it is by default without changing anything. But if one is an expert, it can go down and down and find more and more options that can be tweaked and used at a much expert level. There is also like a learning curve. There is a main initial tab and a final, let's say, cost gathering tab, but in between there are all the different modules of the different technical parts of the system. And we order them in a way that the easiest modules come first and the most complex ones come in the end, so that one can learn as it goes. And the main thing is this comparison availability. In the previous one, you only got one result. We allow the users to implement 3 cases. One of them is a default SPD case. SPDs are system platform demonstrators that come from a different shift-to-rail, or from the whole shift-to-rail framework, from Impact, right? So we created 3 baseline cases based on these SPDs for high-speed intercity and metro. And those values cannot be modified at all. Those are default values that are there as a reference. And if you want to compare something with something else, then you have 2 cases available there for comparison. So you have fields that you can edit. You can introduce different kind of, if something is different compared to your to the SPD baseline, then you can introduce the value there and it will be used instead of the baseline value. So we put a lot of effort on making consistent, using consistent and non-ambiguous language, clear references to different modules, on sections that are the same the whole way from the first to the last tab, And so there's been a lot of effort put into the how the UCM looks and will be used. That is one part. That is the tool. That is the Excel file concept. But then we need to input that Excel file with the so-called performance inputs. We have different modules. I'm listing them here: potential hazards, energy, noise, vehicle maintenance, rail maintenance in one side and ballast in the other side, so they are separated for the infrastructure, and then a final end of life and cost modeling tab. We rearranged them a little bit in order to make them simpler. We added some things that I will go through right now, one by one. The first one that I would like to address is the energy and noise modules, and then there are no changes in the simulation models in those cases, but the economic analysis or the how you calculate the costs from those have been improved a lot. So for instance, the CO2 cost or the greenhouse gas emissions costs have been addressed as recommended by the European Commission handbook on external costs for transport. For noise, there's been also that used in order to be able to address different costs in different areas and different times of the day, so that the nuances of the cost model can be implemented there. Then, in general, wheel and rail damage are something that it's kind of the same in a way, right? They are both sharing the interface, and damage calculation is quite similar from one to another. The first thing we did there was to change the performance inputs to some performance inputs that are maintenance-based. That way, we had reprofiling ore grinding depth and reprofiling ore grinding frequency as inputs in the Excel file. And that makes the Excel file much less complicated compared to the previous one. I will start first with the vehicle maintenance part. There was one of the biggest issues in the previous model was that there were several proposed methodologies for RCF and wear calculation, and that gave a very big spread of results. So one decision that we made in order to select a single modeling method was basically stick to one and use only that one. In order to simplify the implementation of that method, what we did was we created a damage calculation package, a small MATLAB file that is provided for whoever user needs to do these calculations to use that exact package that basically analyzes one contact patch and with the inputs from dynamic simulations can give you the damage, both weight and RCF damage. That way we ensure that everyone that is using the damage calculation part is using exactly the same models, methods, calibrated against the same parameters so that the final results are comparable. There is one point that it's quite discussion intensive, which is if the method for calculating damage is an iterative method, meaning that we update the profile as we go, or if it's a non-iterative one. We went for an iterative method, but there are of course pros and cons for both things to be used. We also simplified simulation guidelines, especially because multi-body softwares have lots of nuances that are different from one to another. So then we tried to make something that is MBS software independent as far as we could, so that anyone with any type of software or even coding their own vehicles in MATLAB or whatever can actually use these guidelines. From the infrastructure side, I already mentioned that we separated between rail maintenance, the so-called rail module, and ballast module. The reason is basically because the maintenance part of the infrastructure just has so many things on top of each other that we couldn't really have one single tab that covered everything and made also like comprehensible and usable in a good way. So we decided to separate rail maintenance, meaning grinding and component fixing and so on, and ballast maintenance, which is more related to tamping and substructure. If we start with ballast maintenance, in the previous model, there was a simulation method that gave you some kind of you could do some simulations with dynamic multi-body simulations and get some settlement values for the track. But actually, all these ballast degradation methods are not very advanced and they're not robust at all. So the decision was to avoid doing simulations for this and just going for a stochastic or an experimentally calibrated method from previous European projects. Then the Excel tool is basically completely different, and the performance input is very simple. It's on Sprang maths. The substructure components and substructure quality are variables in this method, so that it's mostly this degradation, according to literature, is mostly because of the substructure, not because of the vehicles. So it's a very thin line to navigate, because eventually what we want to do is to check what the actual changes in the vehicles do. And with this, you cannot really obtain that. So there is, of course, some follow-up that is needed in this part, but there is a method that is already implemented. The other part is rail, and the first part is grinding. It's similar to the wheel reprofiling part, except that here we could implement a non-iterative method. The geometry is much more simple for rails than for wheels, so the grinding compared to the reprofiling can be done with a non-iterative method, and that simplifies a little bit more the already complex way of calculating damage. Apart from that, the main change or the main introduction in this new model is switches and crossings. And with that, I would like to give the word to Jan Bezan.
Yes, thank you, Carlos. So will share my screen. Okay, so good morning, everybody. My name is Jan Bezan. I'm working for the University of Huddersfield, and I will talk about the switch and crossing part of the module to the UCM. So the interesting aspect is that, as Carlos was saying, the way we started is that in roll to rail, the switch and crossing aspect was not accounted for. So we started really from a blank sheet of paper here, which was interesting. So the first thing was to consider what type of damages we were interested in, and therefore what type of costs. There are things associated with the way the support and the ballast is costing in terms of switches and crossing, and that's integrated into the ballast side of the UCM indirectly as an aggregate for a line intervention. So we focus really on the damage to the switch part on one hand, and things that are related to inspection, maintenance, and replacement, and also on the stock rail. And these rails are seeing a lot of wear, head check, fatigue on the rolling surface, fatigue fracture potentially of the switch, like you see on the screen here, which would lead to eventually to a replacement of the switch pairs. We have an even plastic flow as well, potentially faulty plastic flow that blocks the complete closure of the switch as well. So these things lead to intervention in terms of deburring and grinding. So as I said, the tamping aspect was dealt with in the ballast module. Then in terms of the crossing, again, you have a lot of issues around the wheel rail interface. So you have squats on the casting, misshapen crossing nose, plastically deformed wing rail and nose in the load transfer area, potentially some lipping with material flowing on the side of the rails, and eventually complete breakout of the crossing, like you can see on the screen around this area here on the crossing nose. Eventually, you also get some poor ballast support, and this influences the cost in terms of the rail, because you eventually go into fatigue cracks potentially and broken elements that you then need to replace. So we've considered the crossing repairs and replacements. Eventually, all these things relate really to how the wheel-rail interaction occurs in the switches and crossing, and how the vehicle interacts with those elements. So this is obviously of interest. In terms of simulating or predicting the behavior of vehicles in switches and crossings, we can do that fairly accurately. And we recently published an international benchmark on how to do this using established multi-body dynamic simulation software. And we've shown that we can get good agreements between all the different software. But however, it still remains a very complicated task with a fairly high level of expertise from the MBS user, and it is very time consuming. The main thing is that you have to deal with variable shapes in the rails, in the crossing and the switch, and that takes a lot of time to implement, and it can lead to a lot of errors as well as you do it. So we wanted to try and aim for simplifications, while still being able to assess the vehicle behavior. So the methodology that was used, we considered two approaches to try and estimate how the vehicle behaves in a switch. So the first approach is obviously using the multi-body dynamic simulation, and then try and identify if there are any simple analytical formulas or rules that already exist that are being used, or some that we can actually draw and replace the multi-body dynamics with something more simple. Through the multi-body dynamic simulation, we can evaluate the vehicle behavior through different configuration, like accounting for the innovation that were presented this morning. We can also change the track configuration and the operating condition and evaluate quite a large mix of conditions. Then we can evaluate the vehicle performance in terms of how it produces those damages I was showing before, and then see how we integrate this into the UCM. So in terms of what we decided to do, we try and, as I say, with a goal of simplifying things. The main thing that the vehicle does when it goes for a turnout is that it has to steer from one track to another. And the ability of that vehicle to steer will generate more or less greater forces onto the rails. So we simplified the turnout negotiation with an S-curve, and we inspired ourselves from the EN 14363 Annex F, which tests the vehicle in a fairly tight turnout to look at the imposed forces in curving. And we've done that, simplifying, not accounting for the variability of rail. So we're just looking purely at the ability of that vehicle to steer through that curve. In terms of local forces occurring more locally in the switches, these are, if you take a vehicle for a switch, you will generate some lateral forces as you come to the area where your wheel set will shift over from the stock rail on the left-hand side onto the switch rail. And that generates a lot of the damage I was showing before. And this is the thing we want to capture. So we've done a lot of simulation work through MBS simulation to show that the lateral force generated here correlates quite well with the damage that we're predicting. So for the switch, we've been quite happy that we could then do some fairly simplified simulation. Sorry, going back to the previous one, we've eventually developed a scheme where you replace the variable rail with a simple rail, and you simulate with an additional irregularity. So you can do this very simply, and it takes minutes for somebody who knows how to use multi-body dynamic simulations. In terms of the crossing, we went back to a formula that has been used, proposed, in fact, in the mid-70s and has been used a lot in the railways to evaluate fatigue in crossing, and it's the P24, so it's a dynamic amplification factor that accounts for the vehicle's, essentially the unsprung mass of the vehicle and the speed. It also reacts against the track mass and stiffness, and then it's governed as well by a 2 alpha value, which depends on the shape of the crossing, and the wheel goes through the crossing and goes up and down, and that's what generates a kick and an amplification force. So the scheme that we have effectively is that on the top, we are doing some calculation and simulation, and then we reach back at the bottom where we end up with our UCM performance input. So we've accounted for the switch part. On the left-hand side here, you've got the switch deburring activities we've accounted for. They are tested through the kink simulation with a simplified irregularity. The switch replacements as well are accounted for using this test. And then we have an S-curve simulation at the top there that I've mentioned that allows us to feed into the switch grinding activities. And on the left-hand side, we have the analytical solution with the P2 force that goes and feeding into the crossing replacement activities and the crossing well repairs. In terms of the simulation, the interesting thing is that we can use the complete vehicle multi-body system model. So everything that you have in your model will then trigger the intensity of that intervention that I was showing before. So suspension properties, mass effect from the axle or other part of the system will be accounted for. We do focus the simulation on the diverging route in each case, and then that implies a certain level of damage of the through route as well, but we don't have to simulate it. We've shown that they kind of correlate. In terms of the P2 force in the crossing, the key driver is the wheel set and sprung mass. And then we account for the range of speed that the vehicle will go through on the network and the diverging speed as well, and that feeds into an average value. Okay, one of the things, obviously, we're producing forces, so in kilonewton units. We then eventually have to convert that into our performance input from the UCM, which in that case is an interval of intervention for those different maintenance actions. So they are in million gross ton. So we apply a certain conversion factor. So again, we explore that and we use some reference value provided by TU Graz in this exercise from a mixed traffic network. We did a lot of simulation to find out what was our weighted average for certain range of vehicle, including heavy freight locomotive and passenger coaches. And then that relates to a certain intervention in terms of million gross ton interval to produce those maintenance. And then the user through the UCM can predict either use the proposed SPD values that are used there as a reference, or simulate its own values, and then that would be converted directly to the performance input. So I'll stop here and head over back to Carlos for the following of the presentation.
Thanks, Jan. So that is, let me share again, right? That's how complex you can make the simulation of switches and crossings to a certain level that you don't really need to include the whole geometry. And it's actually really nice results from that part of the research we have been carrying out. And without further ado, I guess, let's go to the actual universal cost model. This is how it looks like. It's not very complex in a way. It's an Excel file, and there are down here all the different tabs that compose the universal cost model. There's a case selection landing page where you have information and you can select what kind of basic SPD you want to use. There is also one tab for each of the things that I've been showing, which we call technical modules. And there is a final tab on results and visualization where the LCC is gathered and the cost benefit analysis is shown. If we go deeper into different, for instance, this is the baseline case selection tab, you can see that as you go down, there are more and more parameters that one can introduce. It's not really necessary to modify any of this, but you are allowed to, and the complexity has been built up so that you can go learning while you read and introduce the different changes from your system, for instance. One of the easiest modules is the potential hazards module, which doesn't have that many variables. You can see here. We have been using the different sections and subsections in a consistent way, so that when you go to, for instance, rail maintenance, which is much more complex, where you do have a number of performance inputs related to grinding, to switch damages and so on, by this point, all the different subsections and so on are the same. They are more complex, they have more information on it, but the sections are the same. So that helps a lot with the comprehensibility and the transparency. We also have pre-calculated things that are included, and you cannot affect those. Those are pre-calculated for different SPDs. the information is there for you to see that there is actually one reference that you can take into account. But for all of these cases, the value of the SPD, it's always fixed. You will always get the same result. And then you can use the case 1 and case 2 in order to see what the differences are. Maybe this is not the best example because I'm comparing nothing here. They all have the same cost level. But in this final LCC slide, I can maybe go back a little bit because all these different columns, right, when it's empty, there you can introduce your own data. There you can introduce your own variables. You can modify the calculations in one or another way by using those available spaces. If there's nothing in, then the calculation is done by using the default values. If you input something there, the user inputs something there, then that value will be used. Finally, we have the visualization part where we do have costs split into operational costs, where you can see what the different weight of these costs are. In this specific case, energy is quite a lot, infrastructure is the second one, vehicle and noise go in that order. You can also have an LCC cost breakdown. You can introduce the cost of the purchase plus the cost of the end of life. So here is investment costs, operational costs, and end of life costs down here. And then you can see for the different cases that you analyze, what is that split, right? You can see that the actual sections are similar or the same as much as we could, even in this last slide. So this is how the UCM looks like, right? So we do have now simulations in one side. We have the tool that will take the output of those simulations for post-processing into a certain cost value. But the thing is, we are analyzing innovations, and innovations is not necessarily existing at the moment. So we needed to at least come up with a simplified method of how should you think about your innovation in order to be able to first simulate what you need to simulate, obtain the performance inputs that you need to obtain, and not more because you don't want to waste your time calculating other things, and then being able to do the cost calculations, right? So we made a quite simplified method based on 3 stages, which is the first one would be what it's called differential features extraction from your innovation. The second one is a causal effect loop on cost generators, or a causal effect diagram on cost generators. And finally, and this is not really necessary, but it's nice to have an identification of system stakeholders and who is affected by each of this. As an example for how you should think about this innovation modeling in this specific case, which is the hybrid composite axle from that we heard from just before, the first thing would be, as we said, this differential feature extraction. You need to know what is the difference, of course, right? From a conventional vehicle, from a conventional wheel set to this type of wheel set, right? So you would have lower unsuspended mass, that's your main objective. You will have probably increased structural damping because it's a composite. So there will be maybe some extra damping there, and you will have modified in structural integrity. I didn't want to say less or reduce the structural integrity, but it could be, right? It could be that it's has less structural integrity or even more, depending on the design. The second step would be to do a causal effect on cost generators, right? What do each of these different differential features, what will this affect? Because you will need to simulate those, right? So in this case, you might think that you need to simulate noise because there is an increased structural damping, right? But maybe with a deeper analysis, you find out that the structural damping is really not that much of this element. So then you can skip that analysis completely, right? And try to focus in what is most important, which in this case, I guess, would be the lower unsuspended mass, creating less wheel damage, less infra damage, and somehow less or a little less energy consumption for the whole vehicle. Then there is these impacts do have some impact in costs, of course, in one or another way. And then in the overall look, right, there is also, these are operational costs. But there are also a difference in initial costs. You will be having as an example here, we said it's 3 times more costly to build this kind of wheel set, right? I don't really know if that's a precise estimation, but that could be it, right? You could have a much more expensive wheel set, and you will definitely have different end-of-life costs. We don't really know how much, but taking care after its life has ended of a composite material is usually much harder, much more costly than the conventional metallic wheel sets. So it's not only operational costs that are changing, but also the other. Finally, it's interesting to understand what stakeholders are affected by this. Maintenance need, right, would be operators and infrastructure managers that will get benefits from. But from these initial costs, right, the manufacturers will be manufacturing something that is more expensive, so it's affecting them in a way. The operators are paying for it. The end-of-life costs are probably going to the operator. So there is a lot of different relationships there that are interesting to understand, even if it's not really necessary for the analysis. This is an example of how you should think about innovations, right? If you come up with a new innovation that no one has thought before, you would be able to do that process and analyze it, while there is no button where you click and say, we include this exact innovation, right, in the UCM. That is not possible, mainly because of the wide variety of innovations that could be. Finally, we did case studies. Of course, we tested this. The first thing that we did was to analyze these baseline cases, because one of the main issues with the previous universal cost model was that it was lacking some information. It was proposing simulation techniques and simulation and calculation techniques that did not have a very thorough cost analysis or a very thorough simulation before them or behind them in order to showcase what they did. So one of the main focus is to find all the information needed, simulate all the simulations that need to be done for each of these cases, which are baseline cases. And then we wanted to test these innovations, right? Or at least they have been saying before me that these innovations in work package 2 and 3 will be showcased in the universal cost model in the end, right? Well, this is the list of innovations that we intend to do for the final report. We wanted to check on hybrid car bodies, which is not part of this project. It's from Shift to Rail, from the technology demonstrator 1.3. Then we have from this project the hybrid wheel set, bogie innovations, and then we have active steering and composite material for the bogie frame. And then we wanted to check on other things that are not really simulation heavy, which are wheel reprofiling strategies, condition-based maintenance, and finally we have as a point there optimized lubrication, or analyzing how lubrication can be introduced in this. But what I will show here now is, and I'm sorry because Stefano said that I would show the wheel set part, but we decided to go for these two cases. So I showed the innovation part with the wheel set, but what we will analyze is these two together, the active steering and composite frame together in one, because it's very difficult to separate. And then we will also show the wheel reprofiling strategies real quick. In this first case, we already seen all this information, right? And we compared one standard bogie with this single axle frame with the composite bogie frame and active suspension. And then from the analysis, it's that we probably have increased probability of hazards because it's an active system, so there will be more dangers inherently. Reduce energy consumption, reduce noise levels, reduce wheel damage, reduce rail damage, and then ballast is maybe a typical, because it's a metro system. It's supposed to be for Metro de Madrid, so there is no ballast to analyze in that case, but it could be very well part of the method too. Here are some really quick results. We have done hazards, increase a little bit, but you see that the cost of hazards is not that much. There is an energy reduction of 14% in the energy consumption with using this method that is proposed in the UCM. The vehicle maintenance of a conventional, or the wheel maintenance of a conventional metro wagon compared to this one For this, it's 2.6 times longer mileage before wheel reprofiling, so it's significantly longer. So the vehicle maintenance difference, you can see that it's very, very significant. There is a slight reduction on noise costs, and there is almost no change, a slight reduction on grinding depth needed, but not that much related to infrastructure itself. So the most changes come from energy and vehicle maintenance. I estimated 20% higher cost than a conventional vehicle, right? In fact, the scenario from Work Package 2 is that the cost will be similar. So considering 20% higher costs, you can see that the investment and the operational costs for a metro, for a conventional one, are split like this, while when you increase these costs and you reduce the operational costs, you can see that the importance of the investment is much more. But in this case, with this estimation, the overall value of implementing this, there is some kind of benefit to implementing this, right? If you consider that it's 0% higher than conventional costs on purchase, at least, these savings will be much bigger, of course. And so one can analyze and scrutinize the different parts where the costs are going, what the different cost benefits are in different sections, and so on. For the wheel reprofiling case, basically it's analyzing what different strategies for wheel reprofiling, how different strategies for wheel reprofiling affect this, right? And the innovation here is not technical, it's just different kind of reprofiling strategies. And it does not affect anything except vehicle maintenance, right? So for vehicle maintenance, the first thing would be to simulate the wear of the wheel sets in order to have this trend and be able to analyze. In this case, what we analyzed was what is called limit flange thickness and flange thickness after reprofiling combinations of parameters, right? So with one of these cases two of these cases that we were comparing with these different parameter combinations, in a way, it's kind of the optimal one and the worst one. You could have a difference, according to the UCM methodology, of course, between the conventional one and the optimal one of a quite significant one, right? I was going to say double, but it's slightly less than that. And now we have discussed everything in a way until we reach some economic values. And the question now is, are these economic values okay or not? Can we validate somehow that these engineering methods work? And then I would like to give the word to Andrew Smith, who will be discussing this.
Okay, so hello everybody, and I guess I've got the pleasure of doing the very last session, so I'll try and keep this one brief. So the background to all of this work is that we know the variability of rail infrastructure costs with respect to traffic is really important because it helps us understand the cost impacts of new technologies, as discussed, and also more widely for the design of track access charges. However, we have two very different techniques, the engineering approach and the econometric approach or statistical approach, which are fundamentally different in the way they operate and have historically produced quite different results. So we've been doing some research looking at how these methods compare against each other in terms of how the method and results that come from looking at this question of how the impact of traffic affects track maintenance costs. And so specifically, we compared the engineering method, particularly one carried out by TU Greenwich University, which is embedded within UCM, as against the econometric method. And what was quite interesting here is we actually had an opportunity because we could compare the two approaches using exactly the same data set, namely data from Austria, to draw some new insights. I should say that some aspects of what I'm going to present are still initial findings because actually some of the data came in a little bit late in the project. I think we can form some general conclusions and also think about where the work could be developed further. Okay, So it's not advanced. Right. Okay, so this is just a quick schematic of the two approaches. So the econometric approach uses actual data on infrastructure costs for different track sections and relates it to traffic, controlling for other factors, and in doing so, produces information on the split of fixed and variable costs and allows us to understand the marginal cost of running extra traffic. The engineering approach, in contrast, works kind of the other way, from traffic through to activity on intervention levels to correct damage, and from there, using a set of unit costs for the activities, the remediation activities that are needed to correct damage, effectively models the infrastructure cost. And underpinning the engineering approach is a lot of information about engineering understanding, judgment, and also looking at data on what actually happens when you change traffic and how does that affect maintenance interventions. Okay, so we wanted to look at how these methods compared, and indeed we had a few hypotheses as to why the results of the two different methods might be different. And the first one was a little bit about the sample selection. So typically in econometric studies, we get data on all of the sections across the entire network, maybe excluding some of the very, very peculiar ones where there's not really any traffic or they're just sidings, or they're not part of the main network. But broadly, we would take the entire network and estimate the model. Engineering methods tend to use representative sections, or in the particular case, the TU-GRATS model is based on a selection of 70 out of 192 sections in Austria. And broadly, these can be seen as the higher loaded sections. And there is a rationale for the selection of those, partly around data availability, but actually also the fact that once you get above a certain tonnage level, you would expect that really the only thing that's driving maintenance from an engineering perspective would be traffic, because you would reach the threshold required for a maintenance intervention before any kind of time-based maintenance was required. So that was part of the rationale for that selection. However, potentially this does raise a question as to whether the results that come from that 70 are applicable elsewhere in the network. And a particular issue that we would be interested in is whether, as you look towards a broader set of sections, you're better able to exploit the variation in the data, see what happens when you get much bigger shifts in traffic. And that might affect particularly the preventative maintenance regimes, which can move in steps as you move from lightly loaded to more heavily loaded track sections. Okay, so just to show some first results, I'll spend a little bit of time explaining this graph because it may not be familiar more generally. So first of all, this is a graph of what we would describe as cost elasticities, plotted against tonnage levels or ton density levels. And we could broadly think of a cost elasticity as being a cost variability, formerly the ratio of marginal cost to average cost. But we can see it, to give an example, if we have an elasticity of 1, that implies that if you increase traffic by 10%, costs would also go up by 10%. But typically in these kind of studies, we see elasticities that are less than 1, so that as you increase traffic by 10%, costs would go up by less than 10%. And if you base your track access charges on marginal cost, which at least as a starting point is the principle behind EU legislation, then typically with an elasticity below 1, you wouldn't recover your total cost. So that's just hopefully to set the basis for the measure here, the elasticity or the cost variability. So just quickly, a second point to notice you'll see is that all of these graphs, which I'll explain in a moment, all of these lines are upward sloping without going into great detail given the time. We expect that to happen, which is reassuring. So just starting with this red line, so this is what happens if we estimate an econometric statistical model relating costs to traffic, controlling for other factors, using just the 70 sections that are used in the engineering approach. And so that produces the red line. Now, the black line is what happens if we use all of the data. And as you'll see, of course, that line looks different. but partly because the elasticity is lower at lower tonnage levels. But if we actually look at the range of the sections for the 70, we also see that it has a slightly different shape. So from an econometric point of view, there's a question: so which one is right? Should we just estimate on a sample of 70, or should we use all the data? Generally, we prefer more data than less. But interestingly, actually, if the worry is perhaps the lower tonnage sections are in some sense unusual, this orange line is what happens if you take the 70 but add a few other higher tonnage sections that are not included in the 70 for various reasons. And you find actually that produces quite a similar shape over this range here as for the line that includes all of the data. Okay, so I think what we take from that actually is that potentially, from an econometric point of view anyway, we would tend to prefer using all of the data. And if we were to restrict our model to just a subsample, the 70, we think that would potentially bias the results. And therefore, potentially also, it might be interesting to look at expanding the engineering approach to look beyond those 70 sections. Just to show what this means in terms of marginal cost or the cost estimates that come from the models, this table shows the engineering model just to kind of disguise the actual underlying numbers. That has an index of 1. So the most direct comparator is this model, which was the red line, comes from the red line on the previous graph. That's what happens if we do an econometric model just on the 70 sections, and we get a marginal cost here that is a little bit lower than the engineering approach. If we use all of the sample, 190 sections, 192 sections, we get a higher figure. But of course, that includes lower tonnage sections. But if we use all of the data, but then just take the marginal cost for the 70 sections, we also get a higher figure. And perhaps the broad point to take from this is that actually, first of all, the numbers are rather similar. So in one sense, we can say the econometric method provides some good cross-validation for the engineering method that's used in the UCM, which is helpful. So whilst the numbers are slightly different, they're not greatly different, and certainly compared to previous comparisons, they're much closer than in previous comparisons. But there are a few points to explore further. And I also just mentioned briefly one methodological wrinkle that we do need to fully iron out is that potentially the engineering method is perhaps producing a measure that's more like an average cost. And so actually here it looks as if the econometric model has a bit of a lower cost than the engineering model. I think once we kind of resolve fully that point, it probably will slip slightly the other way. The econometric method will look a bit higher, but overall, the methods are looking relatively similar, but with some points to explore, which I will now touch on. So very quickly, one interesting point that we've been exploring is that the econometric method can pick up what we would call costs that are generated by traffic but aren't caused by damage. Okay, so the engineering model is of course based on damage, but having higher traffic can cause costs, even if there's no additional damage. Firstly, because depending on the level of traffic on the network, that will affect how easy it is to do possessions access. It will affect the unit costs of the activities done. Secondly, when you've got more traffic on a network, you might be doing more work to prevent, to mitigate delays. You don't want to have delays on busy affections. So although those are important impacts on costs, they wouldn't directly be picked up in the engineering method. And this is a schematic to try to show what we're comparing. We might be comparing two lines with the same amount of trains going down them, the same amount of damage done to the track, but here there are two tracks, and here there's only one, and that has implications for the capacity utilization and the desire to control delay costs and so on. So one final slide before I conclude. Essentially, this slide shows some results of this kind of evaluation. And what it shows is if we're kind of up here, the gray lines, this is where we've got few tracks. so where capacity is more constrained for a given tonnage level, and the econometric approach is producing a higher marginal cost than the engineering approach, as expected, because it's taking account these additional factors. When you go down to the black lines, when you've got lots of tracks, then the econometric model produces lower estimates than the engineering approach as expected. So this is really, I guess, partly confirming the hypothesis that there's something else going on. So although we perhaps find that the econometric and engineering approaches are quite similar on average in terms of the cost calculations, the distribution could be important, and that could be explored further. And we've found similar results, it should be said, using data sets from other countries. Okay, so a very, very quick summary, really. Past research has shown some quite big differences between econometric and engineering estimates. Now, I would actually highlight the Vitism model in the UK, which actually has considerably lower variable costs, and that partly motivated our research. But actually, the part in bold there says, in fact, when we looked at Austrian data, the econometric and the engineering approaches produced reasonably similar results, but with some points could be explored further, and we would produce some evidence on those as noted. And that, I think, does create some suggestions for further research, perhaps expanding the engineering approach to look at low tonnage sections, considering different costs of interventions on different lines, looking at broader jumps in traffic and exploring the motivation to prevent delays on busier routes. And maybe as a final point there in bold, just to note that there are different types of engineering methods other than the one we've shown here today, and further comparisons could take place with respect to different types of engineering methods. Okay, thank you.
Okay, so thank you very much, Carlos, Andrew, and Jan, for the detailed presentation regarding the UCM.
Sorry, there is still like 2 slides from me.
Okay, sorry. I thought that you finished. Okay, sorry, Carlos. Okay, please go ahead.
Here I go. So yes, sorry for keeping you here for more time. I would like just first one slide on the collaboration with Pivot 2, because we have been probably the work package that have more interaction. We did get people for the interviews from the different partners in Pivot 2. We did get also data for measure track damage data for the econometric model validation, even if it's in the end it's not been shown here, and it's been shown the TU Glass case. And especially there's been a lot of interaction in developing models and procedures. So there were initial discussions on the technical possibilities of these simulation techniques. There were some issues we had some internal deliverables and we couldn't deliver them in time. So I apologize for that, but we kind of, after that, we have been working together, instead of going back and forth, going together, analyzing the universal cost model, the guidelines and the procedures. And I'm really thankful for all the feedback that we have been getting. Some concluding remarks. The simulation framework, the biggest point would be that the switches and crossings procedure has been developed. And one of the main things have been, especially when it comes to damage modeling, that the balance between accuracy and simplicity, it's very challenging. So there will always be people that expect more and people that expect less, in a way, from these kind of things. Let's hope that this is the right level. The normalized damage calculation package has been created also, so that everyone that wants to use the universal cost model, the person that is analyzing those results can ensure that if that package has been used, of course, they can ensure that the results are comparable. And we have focused a lot in the simulation guidelines, especially for consistency related to simulation packages and so on. From the UCM tool part, we did integrate all of the post costs in an Excel-based tool, simplified it and made it user-friendly. And we tried to do that systematically using a method, not just going forward to it. One example is that we don't have macros. in this version, so it's a very simple Excel tool. And there's also that SPD-based baseline cases with all complete set of default values, including references, have been included so that it is clear and transparent where that information comes from. I'm missing a point here on the validation, on the econometric validation. We have managed to ensure in a way that there is a point to doing engineering methods like this, and that the results that you obtain are comparable in a way and are adequate to a certain extent. We had some dissemination activities, 3 conference papers, and there are 2 peer-reviewed submissions that are planned, more or less advanced. And there was also a conference workshop on innovation modeling at the Resource Efficient Vehicles Conference. Further work, there is an extensive need for peer review of the tool. It is a very complex tool with lots of nuances and lots of parameters. So I cannot ensure that we did everything perfect. So we will gladly share the tool in order to be able to peer review it. And simulation-based add-on to ballast settlement damage is also required in a way. It's something that the partners in Pivot 2 has insisted on, that ballast settlement is not influenced at all by vehicle design. So then why to include it at all, right? If the tool is for analyzing vehicle design. So then we agreed that we could do some simulations in order to test if we can adjust the dynamic behavior or include the dynamic behavior of the vehicle in that proposal, but we didn't have time eventually to carry through. So hopefully we can do it afterwards. And also the validation of a non-iterative wheel damage calculation method. It's been quite a big discussion on the topic that an iterative method might be too complex, but there are no real non-iterative methods that have been peer-reviewed or have been out there and shown results. So a big project on this, or a big work on this is needed for that. And finally, thank everyone that was involved at some point in Work Package 1. Thank you all of you for your engagement and your contributions. And that's it from my side.
Okay, now it is the time. Sorry, Carlos, for interrupting you before. So yeah, thank you very much, Carlos, Andrew, and Jan, for your detailed presentation, and also to all the people that has contributed to this activity in the project. For sure that there will be opportunity to use this tool, and probably an action that we can take is to upload into the website for the whole community in order to be available and to test it and come with some questions or whatever. So we can think about it regarding the potential dissemination. Okay, so we are arriving to the end. Okay, we are on time. So let me check if there is any question regarding Work Package 1. Okay, no for the time being. But okay, you know, we have a bit of gap between the live of the streaming. So this is what happened with the presentation of Stefano. So we receive a question afterwards that I would like to ask Stefano. Okay, I will read it. Probably the audience can see on the screen. It stated, today the metallic connection and the electric conductivity, okay, between the two wheels is enabled by the steel axle and used for the infrastructure monitoring of free track. How can this be ensured with a composite axle, or is there still an electric conductivity in the composite material?
Okay, can you hear me?
Yes.
Yes, to be honest, that we were not addressing in our work the point of the wheel set establishing an electrical connection between the two rails for signaling purposes and so on. If this is needed, then I think the simplest way is to short circuit the two metallic wheels by a conductive wire, which could be either external to the axle or internal to the axle. In this case, because we have inboard bearings, then routing the wire inside the axle would probably be simpler. Although the inside of the axle should be left as let's say, free as possible for NDT reasons, for NDT inspection. But we didn't really devise a strategy to keep the conductivity of the two wheels.
Okay. Thank you very much, Stefano, for your reply. In any case, if after the conference call, as I mentioned, you have any question regarding the presentation or any specific topic that you want to address to the consortium, don't hesitate to contact us, and we will be happy to reply to all your questions. Okay, so we are arriving to the end. Unfortunately, we don't have more time, although I am totally sure that the partners are really keen to talk more and more regarding all these topics that are really interesting. But okay, there will be, I hope, another opportunity in the future of Europe's Rail. So let me give the floor to Sebastian. Do you want to add something to today's presentation?
Yeah, firstly, I of course want to thank you all for participating in this session today and express the hope that we expressed earlier today also, that we have the chance to follow up some of the innovations presented here today in Europe's rail, and also that the UCM will be started to use as an evaluation tool for innovations in EU rail. And in a little bit longer term, that perhaps some of the innovations presented here today will be part of commercial vehicles. That I think is a dream we all have, that some of the things are really used in the future. And with that, yeah, just thank you all again. Thank you, the whole team, and you who listened here today, and also you, Jose, for your very good guidance throughout the project.
Okay, thank you very much for your kind words, Sebastian. But the merit is not only my merit; it is the merit of all of you, that you make the things simple to me. Also, I would like to remind you that this is something that I think that Javier mentioned during his presentation. I was not here from the very beginning. I started to work in this project after 1 year. My colleague Marta, who left UNIFE, prepared the proposal that, believe me, that this is a really, really difficult moment to prepare a proposal. So also the merit is on her. And okay, for me, the things has been really easy based on the help that you provided to me. So to end this conference call, I don't have more than good words for the consortium, and I hope that we can continue it in the future. Also for Europe's Rail, former Shift to Rail, that with this kind of initiatives, they are promoting the rail transport, also trying to improve the quality of our trains, more comfortable, more attractive, and also contributing to the Green Deal. It means to have greener trains in the European sector. So then this is all from my side. Thank you to all the participants. I hope that you enjoyed our presentation today, and the results would be interesting for you. And okay, as all of you know, the show must go on. So I hope that in the next Europe's Rail, we will have the opportunity to work together for sure with all the partners of Europe's Rail. So thank you very much, and I wish you a good afternoon.